Good morning. I'm Jean-Louis Van Bella. I am from Belgium. I posted a few videos before on YouTube, and you can also see I have published some stuff on the web on ResearchGate there, and then a lot of papers on the side of Phil Gibbs, and then I also have a few blogs on physics. So yesterday, actually, I gave this presentation for a small group of students who are trying to model electrons and Stern-Garg like experiment and interference. And so I thought I would upload this video to YouTube. It's quite long. The feedback I got yesterday is that it's too long and that I should start by a summary. So that's what I'm gonna do. So if you switch off, then at least you will have had some kind of summary. So this is the summary. Um, this looks very complicated, and it is. The the topic is actually an interpretation of the Broglie wavelength. So what is that, the Broglie wavelength? We know it's the ratio of Planck's quantum h and the momentum. So it's kind of weird because if the momentum is zero, if an electron is at rest, then the Broglie wavelength becomes infinity, right? Because we have h divided by zero, mass times velocity is the momentum. So we have a wavelength that becomes infinity. And there's also something special about it. If our electron moves at light speed, then the Broglie wavelength becomes the Compton wavelength, the Compton wavelength. Sorry, I always say Compton, but he's the Compton wavelength. Because then you have the Broglie wavelength, h divided by p, h divided by mc. H divided by mc is the Compton wavelength. So the Broglie wavelength varies between infinity for an electron having zero velocity and the Compton wavelength for an electron moving at the speed of light, which of course it can never really move at the speed of light because it has a mass, so we can't bring it up to the speed of light because its mass becomes heavier and more massive. So the Broglie wavelength is a funny thing if we try to imagine what it really is in 3D space. And that's what this whole presentation is about. I'm going to offer sort of a different model of the matter wave, basically. Matter wave for an electron or for any matter particle. So what you see on this slide here is on the left, on the top there, you see an equation which involves three wavelengths or three lengths, because as I will show in a moment, you shouldn't really think of these lengths necessarily as being linear. But it's a funny formula actually, and we'll get there. I'll show you how I get that formula. The three lengths that you have there in that formula are the first one is really the Broglie wavelength, which I denote by lambda p. I use that subscript p because the Broglie wavelength varies, depends on the momentum p, right? So if the momentum is zero or something between 0 and mc, then the Broglie wavelength will be different. So it is a function of the velocity of and the momentum of the electron. So I have lambda p. The second lambda, which doesn't have a subscript, people said you should give it a subscript, but I don't know, is this lambda. Lambda is a linear is a linear length. If you see that weird Archimedes screw underneath it, we have four situations there. We have like the black thing, the black ring. In the very beginning is an electron at rest. An electron at rest, it's a circle. You'll say, yeah, it is a circle, because what we're going to use in this presentation actually is a ring current model of an electron. We're going to think of an electron as a charge spinning round and round and round. You may think that's a funny idea, but actually the ring current model has been around for forever. It's more than a century old. It was first so in the beginning of the 20th century, I think, almost the same time when Einstein published his special relativity theory in 1905. Because the idea was a bit, and that was even before the magnetic moment of an electron was discovered, that um, electrons do have a magnetic moment, and so that must be generated by some kind of current, a ring current. And so that ring current model has been around forever, and it's kind of strange that it hasn't been developed into something more. And Schrödinger and picked up on it as well, because he saw a ring current model for an electron actually is a very trivial solution to the wave equation for electrons that was developed by Dirac in 1927. So it's not a stupid model, and it's quite subtle. And David Heston has revived it in the 1980s, and so yeah, it's picking up speed as sort of an alternative interpretation of mainstream quantum physics. But to go back to the illustration there and that formula, when our electron starts moving, and I indicate some relative velocities there, we get that sort of, I don't know what that color really is, something between something bluish. Indigo, I think it is. So then the motion of our charge becomes indeed an Archimedes screw. An Archimedes screw, sort of to pump up water. It's that spiral-like thing. So our charge that goes round, round, round in the black. The electron at rest there, we add a linear component to the motion, to its motion, and then we get that Archimedes screw. And so the first one gives the motion for a relative velocity that's equal to 0.43. So the ratio of the classical velocity of the electron and light speed is almost half. All right, and then a funny thing happens, and I will explain why that is. It's actually the idea is very simple. You can never, nothing can go faster than light. That's what clearly comes out of relativity theory. And so if we add a linear component to the motion of our charge, then the radius of that oscillation has to become smaller. Think of it of sort of dividing a bit the light speed over a linear component and a circular component. So if it goes faster and faster and faster, our Archimedes screw becomes, has a smaller diameter, and you have the brownish thing there for a velocity of relative velocity of 0.86, and then the reddish, the red one. It's almost light speed there. It's 0.96. So that's the idea, really, that we're going to look at that illustration, which I have to credit a bunch of Italian researchers for. I'll come back to them and mention their names and the articles in the presentation. Really very creative guys. So we're going to basically talk about that illustration and sort of explain its shape and how it changes. And that's what's in that formula, really. The lambda, to come back to that formula, the product of the two lambdas that is equal to some other lambda squared. The lambda without the subscript is actually, the distance between, I would say, like two crests or two troughs in the wave. It's a linear distance. But yeah, because of that, the oscillation is two-dimensional, so we can't really talk about crests or troughs, but we can talk about the distance between 2 points where the value of the wave function is the same. So you see here the value of the wave function. It's a two-dimensional wave function. We have we can split it in two components, a horizontal component and a vertical component, or we can move that around. Because we can describe it as the sum of two components, and then the values, so that's it. We could think of it as a vector, will be the same between 2 points. You can see that it makes one circle, and then it moves a bit while it does that linearly, and then it arrives at the same horizontal and vertical position. So that will be the second lambda. If you've lost me already, then yeah, I'm sorry, but yeah, maybe it will become more clear than later. So that the product of the Broglie wavelength, that's what we're going to show, and that linear length is equal to the square of the third wavelength. That's the Compton wavelength. Again, I will say Compton because it's a very French word, but Holy Arthur Compton was an American, of course, and that's the formula really. The Broglie wavelength times that linear length that describes our Archimedes screw is equal to the Compton wavelength, and the Compton wavelength actually is really the circumference um, of that black circle. If our electron is at motion, is not at motion. Sorry, if it's at rest, we have that black circle, and then the Compton wavelength is going to be the circumference. And that circumference, as I said, it sort of becomes smaller as our electron starts moving linearly. So that depends, of course, on your reference frame. In its own reference frame, it's always at rest. But for us, we can see it move, and then the Archimedes screw becomes scratched, and the radius of the circular motion becomes smaller, so the circumference of that circle becomes smaller. But what's going to be the case is the product of the Broglie wavelength, which also changes with motion, and that linear length is going to be equal to the square of that circumference of the orbital motion. And using natural units, we may also not use natural units. Then we just have h and c that get added to the ratio at the end. But it's equal to 1 over the square of the mass of our electron. We're going to show that too. Now that looks like a very simple formula, but it also looks like hocus pocus, and what is it? And so that's where this formula is actually a lattice rectum, the lattice rectum formula for an ellipse. You see an ellipse there in the middle, and you see that little formula, the product of some length a times another length p is equal to a squared b, and you can see what these three lengths a, p, and b mean just by looking at that ellipse below. So I could call one a lattice, and then these have there are a lot of Greek words. The math of ellipses is quite fascinating. We have a number of analytical formulas, but for instance, to calculate the circumference of an ellipse, there's actually no precise analytical formula yet. So there's a few subtleties there that are really interesting. This lattice rectum formula also goes back in time to Leibniz, and so that's the time of Euler and all that. So it's a fascinating formula that we think we have some kind of realist or real description of what an electron actually is, and how it moves, and how we should model this matter wave, because it is an oscillation and it's the matter wave in 3D space and in time. And we see that we need a pretty complicated set of lengths to sort of describe that wave, three wavelengths, or lengths actually, I said, because the lambda is a linear one, the Broglie wavelength, I will talk about that in a moment, what it means geometrically, and then the Compton wavelength, we know that's a circumference, so that's not a linear length, but they are lengths, all right, and so they obey that lattice rectum formula. They're exactly the same. Just sort of to say how that differs from anything you've ever heard about quantum physics. On the right hand side of this slide, you have the quantum mechanical, the mainstream quantum mechanical explanation of an electron or a matter particle. It's that for me it's a weird business. We have the Broglie wavelength there. We sort of do assign a wavelength lambda, a Broglie wavelength that is equal to h divided by the momentum, or second Broglie relation is just p is h divided by lambda, so can switch around, and then we're gonna, not us, but the Broglie thought of Yeah, clearly some kind of linear waves. I'm saying waves because he thought of a wave packet. We think of an electron as a wave packet, so it's basically the sum of a lot of waves, wave components, component waves, with slightly different frequencies and therefore, when you add them, you do get a wave packet, and it's localized, the wave packet. You can see that the sort of um, position in space is given by, our uncertainty on the wavelength, the delta lambda there, and so it's localized. But the nasty thing about this kind of logic is that um, if you have different waves making up, one wave packet, then we will have a dispersion relationship that gives sort of, and so we have a quantum mechanical dispersion relationship. It relates the frequency to, the velocity of the component wave and its wavelength and if you start doing that, building wave packets from component waves, you can have a really well-behaved wave packet that sort of sticks together and travels in space. But the funny thing is, the logic and the physical equations, like the Planck-Einstein relationship, if you apply these to these component waves, then you get a dispersion relationship that gives us a wave packet that is not well behaved. It disperses. It disperses. That's why it's called a dispersion relationship. It sort of dissipates in space. It loses its shape, and so the funny thing is that everybody looks at that and says, "Yeah, fine, yeah, we know that." But when you think about it, a real life particle, an electron or an atom or whatever matter particle you can think of that we model using such a wave packet, it doesn't dissipate. It stays together. Atoms and electrons, they go through a slit or two slits and they behave funnily, and we think sort of, yeah, one electron going through two slits. So they're actually, we may think at that the really tiniest of scales that an electron might somehow split when it goes through splits, but that's not really a fundamental change in its shape or in its integrity, because at the other side of the two slits, there will be a detector screen. We'll look for the electron and we'll find it. It's not gone. It sort of arrives as a lump of energy or whatever at the screen, and so it doesn't get lost. It doesn't dissipate. So the mainstream interpretation of a matter wave or an electron itself, the model that you have there, is weird for a number of reasons. I would say it's weird because, of course, what we have there at the bottom, on the right hand side, you really have all these questions in regard to what is that oscillation, what is the real and imaginary part of the wave function. We model it there, but what is the physical dimension? The shape of the wave looks like an electromagnetic wave, so maybe you wanna link it to the electric field vector and a magnetic field vector, and you can do that actually, but mainstream quantum physics, they don't do that. They say like, well, we don't know. Um, we don't need a dimension. We just have these quantum mechanical rules that say, when we have two two different paths, then we will associate a wave function with these two paths, and we will then add the amplitudes, and then we will take sort of the absolute square of the sum of those amplitudes, the square of the absolute value, and then we arrive at a probability distribution. So you have that logic and story that um, sounds very intriguing and mysterious, and if you repeat it long enough, then you sort of feel like, yeah, I kind of get that, but you never quite get it completely. So that's the story on the right hand side, and our story on the left hand side, with that Archimedes crew, we'll try to show that that's a story that is much more real and and easier to understand, to visualize, and whatever. So it is an alternative interpretation of quantum mechanics for sure, that we're going to bring here. And yeah, so we'll start with it. And the bottom, you see that, oh, I still got some other stuff there, still more transverse wave and a longitudinal wave and omnidirectional pulse. What the hell is that? And a transverse spherical wave. I just add these animations to show that you know, in your course of physics, you will model very complicated waves, of course, and wave shapes. But even then, you know, there's like a lot of simplifications in a lot of courses. You know, they will model a transverse wave. What would I do there? Like, but that's one in 2 dimensions. In 3 dimensions, all right. Some kind of plane wave in 3 dimensions, right? Or a longitudinal wave in 3 dimensions. And you can see in 2 dimensions how complicated things get if we think about, you know, combining these somehow, or thinking more like a pulse that originates somewhere, which you have in the third animated GIF there, or that transverse spherical wave. You see, just in 2 dimensions, things can become very complicated. So in 3 dimensions, things get more complicated. And I just want to show that, you know, thinking of a wave that is slightly more complicated, like the wave shape I have in my illustration there, which the Zitterbewegung trajectory. Zitterbewegung is a German word. It's Zitterbewegung ring current model of an electron. It's used interchangeably. There's a few different models within the model, but basically, yeah, a charge that is, you know, tittering around. It's a German word. Titter means oscillate or shake or tremble very fast at light speed. Actually, we will argue in a moment. Then you know, you can do a lot with that, especially because I said you have like 3 lengths to that sort of define that wave that are interrelated. Okay, that's a 20-minute talk about 1 slide already, I see. So I guess I've lost a lot of people already. But yeah, that's what it's about. Let's move to the next slide. So we'll start a bit with a bit of history here. We know, of course, light is a wave for sure. Well, actually, it wasn't that obvious. We all know Newton, and you probably heard that in some course, but you forgot about it. Newton actually thought light consisted of little corpuscles, you know, little particles. So it's funny because, yeah, what we know now is indeed, you know, yeah, light is a wave. But yes, it's also a bunch of photons. So the photons arrive and they behave wave-like. They interfere with each other, and what's even more remarkable, if we send photons one by one through a slit, then they sort of interfere with themselves and maybe with the slit. I mean, a lot of funny things. So it's wave-like and it's also particle-like. But yeah, usually we think of light as a wave. Why? Because we're really, you know, we see interference and diffraction phenomena everywhere around us, and especially, you know, it's easy in a lab and you know, with lasers and stuff. So we think of light more as a wave than as a particle, although we have you know, the photoelectric effect and all that kind of stuff. So it does behave like a particle. But just to remind you that that was kind of a revolution around 1800 when Thomas Young, he was actually a medical doctor studying for medical doctor in Göttingen. You know, these people, they studied various disciplines, and it was a Renaissance thing that you can you know, understand various disciplines and so in Göttingen, he started working actually on a theory of sound waves, and then he just applied it actually to light, and did that experiment that you see there, that illustration figure 442. That's an illustration from the paper he then later wrote in London for the Royal Astronomical Society, where in the middle you have the 2 slits, and then something. Well, they are actually separated by just, you know, a playing card you use in to play cards. and then a light beam that came through a little hole in his curtain of his room, and he saw a diffraction pattern on a screen. So that's that figure, and then he made a lot of nice drawings on at the bottom there how it could be modeled. And on the right hand side there you have a much more modern picture, obviously made much more recently, of a light beam. It starts from a point source, so it's a spherical wave. We think of it as a spherical wave at least, and then it goes through two slits, B and C. Starts at A, and so it goes through two slits, B and C. And then we have two new point sources. That's how we think of it. At least, I mean, the reality is, of course, a bit more subtle, probably, because if you have a slit, there should be probably more than one point source for each slit, and what determines then how many point sources you have, and there's a whole lot of stuff that links to the width of the slits and the distance between them, and etc. But basically, that's how we sort of think of interference and diffraction. The two waves that come out of these two slits will interfere and produce an interference pattern on the screen F, and it's shown here on the right. You have fringes and secondary, tertiary. I mean, you have a lot of peaks and troughs. So light as a wave, yes, and at the same time, I said we revived. Planck did that, and Einstein more. Actually, Einstein was the one who wrote that famous paper in 1905 on the photoelectric effect. Light is also a particle. So in the meanwhile, later actually. So in the 20s, there was really the birth of modern quantum physics. We had these scientists that were analyzing the surface of a piece of metal, nickel, to sort of even if you grind it and if you make it very flat and shiny and polish and whatever, it will still have a structure. And so they thought, okay, let's analyze that structure of nickel metal, as polished as it is, but we'll fire electrons at it to sort of see the deeper structure. How does that look really like? I mean, it's just like studying a crystal. A crystal, don't think of diamonds here or emerald or whatever. No, it's metal has a crystal structure, a very regular structure. The atoms are organized in molecules, and the molecules are organized in a very neat lattice structure. And so when you want to see how that really looks like, you can fire photons at it and then see how they diffract, right? And but what these guys did is, let's fire electrons at it and see how they, diffract. That was their surprise. So they bounce back and come back in all kinds of angles, and but they really behave like light. There's a diffraction pattern there, so there's like secondary. There's more orders of diffraction and interference, secondary peaks of intensity and tertiary peaks, and so they saw electrons diffract, and that was weird, So they didn't just see like normal scattering, but really behavior, light-like behavior and diffraction. So I write that there. This Davison in Germany, they got a Nobel Prize for it. You can see on the right there. And at the same time, just to be true to history, we had other people doing similar experiments who are maybe not so well known. There was one in Scotland, the University of Aberdeen, George Paget Thomson. It's another Thomson, and the Thomson from the Compton Radius. But they found the same thing, that electrons, you fire them at that thin metal film. They go through, or they don't go through, or they bounce back and whatever. But they do show more than just an elastic collision. They also show a diffraction pattern, and so that's at the same time. Einstein was he was quite young in sort of 1905 for sure, and when he was invited to the first Solvay conference in 1911. He met a young guy there, Louis de Broglie, from noble and a very noble French family. How did they meet? Actually, I mean, first Einstein himself in 1911 was invited to that very first Solvay conference by Hendrik Anton Lorentz, a Dutch physicist whom you know from the Lorentz factor and these formulas for the transformation of coordinates and time when you go from one reference frame to another, and you want to do it in respect of relativity theory, then you will use Lorentz transformation formulas. So Lorentz is he got a Nobel Prize and all that, very famous physicist, but you know, people have a bit of a wrong view of him in terms of, you know, defending classical electromagnetic theory and having it all wrong in the end and whatever. But he was quite a character, and he acted as a bit as a mentor in many ways to for Einstein. Einstein described him at some point in time as sort of you know, a father, and you know, a very strong support. And so actually it was Lorentz who invited Einstein in 1911 to the very first Solvay conference. You will say, what, you know, what's Louis de Broglie got to do with that? But I'll come back to that in a moment. So Einstein was in 1911. He was really well known, but he was also like, you know, not all people were accepting his theories and this and that. So it was really Lorentz. I said we think of him as sort of a representative of old classical theory, but he and Einstein actually got well along, and you know, in later writings, you know, Lorentz didn't have an issue at all with Einstein's relativity theory, and he actually insisted that Einstein should participate in the very first Solvay conference on physics. And at the same time, so Einstein was there. This Louis de Broglie was a very young guy then, I think 17 or 19 years old only. And his older brother, Maurice de Broglie, was already a very famous physicist at the time. A scientist, because like I said, these guys sort of you know, moved between chemistry and physics and math, and very fluidly. But his older brother, Maurice de Broglie, was there from the beginning in 1911 and later. And so Louis de Broglie, his younger brother, was very interested in physics and this and that. So Maurice de Broglie took him along, and he, you know, they gave him the place as a scientific secretary in these Solvay conferences. So Louis de Broglie, you know, was really aware as a very young and bright student of all these developments. And so Einstein already had told Louis de Broglie as early in 1911, a little bit like, you know, we think of light as a wave, but you know, yeah, it's particles as well. And so now we have the problem if we think about matter. You know, we think of matter as particles, but you know, they also show now wave-like behavior and whatever. So you know, how do we think of matter particles as waves really? And so they discussed and chatted and this and that. And actually, so Einstein really very strongly supported Louis de Broglie when he came out in 1924 with his PhD thesis, which basically jotted down that equation there. We will associate a wavelength lambda, is very bold, with all matter particles, and so this wavelength, we will link it to the that's what he jotted down. Where does it originate from? You know, it is consistent with a few other formulas like the Planck-Einstein relation and whatever, but basically it was a bold, just a bold formula. And I'll show what makes sense and what doesn't make sense of that formula. But yeah, lambda, the Broglie wavelength, is the ratio of Planck's quantum divided by p. And so yeah, we have a wavelength that's related to, you know, the classical momentum, and uses Planck's quantum of action. So the question we will want to think about today in this presentation is, you know, what is this de Broglie wavelength? What is it really? How should we like imagine it? Because I said it is kind of a weird thing, you know. The if the momentum is zero, so in the frame of reference of our electron itself, or if, you know, if we would be able to take an electron and keep it still, just it's there, tap. So it doesn't move in space, then its momentum will be zero, right? Kinetic energy will be zero too, because the velocity is zero. And so the mass of the electron will be its rest mass, and but in that formula, the rest mass of an electron times zero is zero, and h divided by zero is, h is very, very, very small, but if you divide it by zero, you still get infinity. I mean, you take a limit here, and it's an infinite value. So you have an infinite value for a wavelength. Infinity in physics and math is nice and has a meaning and all that, but the meaning of infinity in an equation like that, when you get it out of an equation, you really need to think about the context and what's going on, and it doesn't tell us very much. It's really shows us that something is maybe not right in our model if we can't we can't really imagine what infinity is in well, why does the Broglie wavelength become infinity? And then on the other hand, if an electron, and we know it can't happen because it has a non-zero rest mass, but if we would be able to accelerate it, accelerate it more and more and more, and it would sort of go to a velocity that equals or is almost equal to the speed of light, then we get the Compton radius or Compton wavelength. Wavelength if we take h, and we get a Compton radius if we would take h bar, if we divide everything by 2 pi. So then the Broglie wavelength becomes this Compton wavelength. So what is the Broglie wavelength? We know it varies depending on the momentum of our particle between infinity and the Compton wavelength. But yeah, what is it? Because we're talking about the length, right? It is in the end something you express in distance units. And so yeah, we want to imagine a length. It can be the length of indeed a circumference, or it can be a linear distance, or we can measure something along some other curve, a weird shape, but it's a length is a length. It's a distance between 2 points, maybe not necessarily measured along a straight line, but it is a length. So we need to sort of wonder what we can imagine. So meanwhile, while the Broglie and in Brussels in the 20s, or sorry, in Paris, but in Brussels when he was there for the Solvay conference in 1921, we had one. 1927 is more famous and in between, but 1921 and 1927 Solvay conferences, as you know, were really determining. So all these scientists in Europe were thinking about that, and then Compton was doing experiments in the US, and we had Jemison Davison experiment, and then there was another experiment here. Well, yeah, I already mentioned it. Compton, Arthur Holly Compton in Washington University in St. Louis. We mentioned Scotland, but now we have Missouri. He was there. He did this experiment, which actually brings electrons and photons together, and it's sort of you know that you've seen that in your course. We can fire, we can just aim a beam of light. But think of it of firing photons at some kind of material substance. You see there was a graphite target. So the photons hit electrons, because the electrons are in electron orbitals around some positive nucleus, but the photons will interact with the electrons. They will not interact with the nucleus. So we have an interaction between photons and electrons. And then what we already knew is that mostly the photons will scatter elastically. There's no change in the frequency. Usually, that's Thomson scattering. That's sort of like the classical scattering of a photon. There's no change in the frequency, but so Compton found that X-ray light, and it depends a bit on the energy, and you see a different effect when you use X-rays. You see that the photon get scattered, or these photons get scattered, but they're it's just like it's not the same photons anymore. What seems to happen, and that's how we mainstream theorists will not say that, but what seems to happen really is that there's like some kind of absorption of the photon by the electron or by the atom, and then it emits like a new photon with a different wavelength, slightly different wavelength. So we get an incoming photon and we get an outgoing photon and some angle. And you can see that at the bottom there on the right hand side, we have the wavelength of the incoming photon will be some lambda, and then lambda prime will be the wavelength of the outgoing photon. And then there's an angle. Based on that was the other thing. So these experiments were done, and you measure the angle, and the Compton was measuring also the difference in the wavelength. You can do that if you wonder how you do that. That's sort of mentioned there. You will have the photons that come out of the graphite target will hit then another crystal, and they will be scattered there. Classically, actually, and the Bragg scattering, and then we can measure their energy based on the angle of scattering. So, I mean, that's a complicated setup, and I'm not going to go in detail, but that's really the idea. You have photons of a very precise and frequency, and then the photons that go out have a range of different frequencies, and the frequency will be different, but this formula will apply, and that's where the Compton wavelength comes up. You have another length there in that formula. The difference between the frequency, the lambda prime, and lambda, the frequency of the outgoing photon and the incoming photon, will be equal to what you see on the right hand side of that equation, 1 minus the cosine of the scattering angle. And h, that's the factor there that pops up, h divided by the mass of the electron. It's not the energy of the photon, but the mass of the electron. And c, so h divided by mc, and you can work out the physical dimension of that thing. H is Planck's quantum of action, so it's a force times, so expressed in Newton, times a distance unit and a time unit, and then mass, if you write that in terms of force times, use Newton's formula to get rid of the kg, the kilogram, and you write it in terms of force and distance unit and a squared time unit times velocity, you will get a length, all right, because 1 minus cos 1 minus the cosine is just a scalar. It doesn't have a physical dimension, but you will get a length. You will get something that is expressed in meters. So h divided by mc is something expressed in a distance unit, and on the other side also we have a difference between two wavelengths. So we have a length there, the Compton wavelength. And as mentioned in the beginning of this presentation, that's the other question that we want to think about today, is that what is this Compton wavelength, and how does it relate to the Broglie's wavelength? Now, if you looked at your courses, depending on which course you have, because a lot of courses really don't talk too much about that, because again, it's a bit of an alternative presentation, and are we really sure what we're saying? But h divided by mc, this Compton wavelength, vaguely we do think of it as sort of some kind of area of interference. When that interference or interaction happens between the electron and the photon. So we fire a beam at an electron and say we don't really know what an electron is, and it's this weird quantum mechanical thing, and depending on what you believe in, you will say it's a wave packet. Or what I do more is I believe it's some kind of a charge in motion. And so, but whatever you think of an electron, what it might be or what it might not be, you will have in these experiments in an area of interference. There's some kind of 3D or 2D, 3D space or a 2D surface, an area of interference. And the Compton wavelength is surely related to that. We might divide it by 2 pi or multiply it, or use the formula for a sphere, but it will pop up in the formula for the area, the effective area of interference, where this interaction happens between photons and electrons. Just to talk a bit more about the idea of an electron here, because we will need to think about that. And if you don't have like some kind of idea what we might be talking about, or some kind of imagination, then all the formulas are going to look very boring, and you will switch off if you haven't already. I think I'm gonna talk I now because it's really my interpretation here. I really think of an electron as a point-like charge in motion, tittering around locally. As Schrödinger discovered that, really, that he said like, yeah, there's, and it makes sense because Compton in the 20s, the papers that get published, and I will show a few of these. I mean, at least the first page, and mention a few names and what happened when historically. They were very much thinking of this thing of an electron having like 2 radii. You normally, if you think of a particle, you will have it has this size, one size. But here, no, it is not one size fits all. It's when you do these photon electron experiments, you have electrons, that are in some target linked to or electrons in free space, and you fire photons at them. It looks like sometimes there's no frequency or wavelength change of your photon. It hits some kind of hard target, and that's the tiny classical electron radius. So we think of the point-like charge itself is very small. It has the dimension, but you know what it is? It's the classical electron radius. It's a few. It's expressed in femtometers, and it's really small. But then we have a second radius or dimensional size of the electron, and that's this Compton radius, a wavelength. There's that length describes an effective area of interference, which is much larger. And we know that Compton wavelength and the Thomson, well, we call it Thomson radius, but they're linked through the fine structure constant. So that's the fine structure constant, that pops up in a number of situations. Also, when you describe atoms and you go to the Bohr radius, then the electron in an orbital around, circulating around a nucleus, becomes again much bigger. Like it's the electron goes around and around. We think of it as some kind of cloud thing, and the radius that describes that space in which our electron is supposed to be orbiting, whatever it means, because I said we think of the electron as some kind of cloud but and then you have the probability and distribution described, solutions that come out of Schrodinger's equation and all that. But we have 3 radii, I would say, the classical electron radius, and then this Compton radius, and then the Bohr radius of an atom. But so an electron is a funny thing because it appears in different sizes, so to speak. And why does it do that? Well, in my model, it's really just because we have motion within motion. But the main motion is really that Zitterbewegung motion, where the electron for me is a point-like charge, much smaller, that generates the because it is in motion, generates the magnetic moment of an electron and all that, and so the real radius is it is a classical electron radius, but the important radius here in these kind of experiments is really that Compton radius. So that's then the size of an electron we should think of. It's a funny model because it's actually an application of John Archibald Wheeler. He was a very famous physicist, and he had these ideas that we should be able, mass is a mass of inertia, measure of inertia. But he said mass basically, if you look at the energy mass equivalence relation to Einstein's equation, E is mc squared, he thought of like, it's really everything is energy. And so we should be able to have models which he called mass without mass models, where all of the mass of an electron or particle is really in its energy in some oscillation, and then mass will measure is a measure of inertia for that thing that oscillates. And that makes sense because, you know, if you have like a spinning wheel, you know, think of a bicycle wheel that you're holding in your hand and you're spinning it around very quickly, you know, it becomes very difficult to move it well, in certain directions, and a bit easier to move it in other directions. If you want to change the plane of that oscillation, for instance, if you hold it in your hand, it's spinning around on your hand, then I don't know if you're a cyclist, but I do that. I sort of tune wheels sometimes, and I spin them around in my hand, and then you see all kinds of funny things happening when spin is involved, angular momentum is involved. You know, there's precession. You will see that. You will feel it in your hand when you hold the axle of a spinning bicycle wheel, and then you can see it's much more easy to move it like in the direction of you know, the angular momentum vector than it is in than to change that angular moment direction of that angular momentum vector. So to change the direction of spin requires more energy than just moving it in the same direction. That's sort of all we're gonna say at this time. So just take this away. We here have you know, these experiments in the 20s that bring, you know, our mental concepts of what matter actually is and what light actually is together in some kind of in between wavicle like description. So here we're gonna talk about very recent experiments and what's actually measured. I'm just sipping some coffee here. What do we have here? We have that you know, images from a very famous experiment. I don't know why these guys did not get a Nobel Prize yet. In 2012, this group of scientists around Herman Batelaan and his mentors and his crew and a few other universities, but basically the University of Nebraska-Lincoln, did Feynman, you know, the Feynman lectures, right, in 1963, and it's sort of the standard, yeah, the standard description of how interference between electrons happens, this double slit experiment and that kind of thing. So you have that on the right hand side there. You have and the illustration comes from Feynman's lectures. You have an electron gun that just like, you know, some kind of apparatus that fires tennis balls, or I don't know if you can fire baseballs, but tennis balls for sure. If you train, then, you know, there's a machine on the other side of the net that fires tennis balls at you in a range of directions, but, you know, usually fairly precisely. So the range is pretty small, and then it goes through. It's aimed at two slits there, and so the electrons go through the two slits, and then you have a mask behind. You can see that mask. M-A-S-K, and that mask, you can move that, so you can cover one slit and you can cover both slits, and you can choose which, if you want to cover a slit, if it's like slit 1 or 2, and etc. And you can move that mask around and then see, because you have a moving detector at a backstop where those electrons then crash, which measures where they crash and what the pattern is, the intensity, you know, how many electrons arrive here and how many electrons arrive there, and then how many electrons did I fire. So then you take the ratio and you have an intensity. So many electrons, so much such percentage, think of it like that. So that was a thought experiment when Feynman wrote about that, and other people. But in 2012, you know, we have nanotechnology. It's just amazing, and that's the two insets there, number 1 and 2. If you see that, you have, you know, this nanometer technology allows us to mill really thin films or material objects that, and then we can have a slit. Put a slit in it, and you see in the middle there's just a bit of a support. It's not a slit within two slits within the two slits. The two slits are horizontal, and so in the middle you have a little support there, just to make sure that the width of the slit is remains the same. But That's really amazing. Those slits are 50 nanometers wide, and you say, all right, okay, so what? But that's really a distance we cannot imagine anymore because we're used to like adding, 100 plus 1000 is 1100. But when we start multiplying or dividing, 10 by 10 by 10 by 10 by 10 by 10 by 10, you can't imagine that anymore. Here, there's this story. I don't know what the background is, but I think it's a beggar that sort of has some says does something for a king, and the king says, or has to do something for a king, and saying, well, what do you want as a reward? So the beggar asks, so like, I have a chessboard here, 64 um, positions, and so I'm gonna, move, in the first position, you give me a grain of rice, and then when I move to the second position, you just double. I get 2 grains of rice, and then I get 4, and then I get 8, and I get 16. And so, yeah, at the end, position 64, when I've gone through all of the chessboard, then I'll just take that rice home, right? And then the kings, of course, said that's cheap. But when they started calculating, they actually saw that so many grains of rice is not even. It's not produced in my kingdom. It's not produced in the world. It's just such a massive amount that he couldn't reward the beggar. So here we have the same thing, extremely small things. And so that's the amazing thing about physics, that we can actually do these things and think about them while it's so much smaller than everyday experience indeed. So the mask is the same thing. You see it there. It's that black thing. And you see 2 micrometers there, but yeah, these things are incredibly small. So the slits are 50 nanometers wide, 4 micrometers tall, and then you get on the left-hand side the what happens and you have a series from top to bottom. 1, 2, 3. How many? You have about 10 there. So on the top there, there's an inset there too. You see the mask, and it covers the 2 slits. The 2 slits, if you go down, there's these little white things in the inset. Just stare at it a while, think about it, and you'll hopefully recognize it. I don't have a pointer here, but you see the first one. So the top left illustration there, which mentions 2760 nanometer, because that's the width of the picture that is taken there, so to speak. It's black, and no electrons get through because the 2 slits are covered. And then we go down, you can see the mask has moved a little bit and is partially uncovering 1 slit, the left slit. That's what's in the inside. And so we have some electrons going through, so we start seeing a pattern. Just to repeat again, so the pattern gets built up in time. This thing, because there has been experiments on electron diffraction and interference before. I said Dave's in German experiment was one, and that was in the 1920s, right? But that was a lot of electrons, and a lot of electrons, because they didn't have the technology to sort of fire electron one by one. They had an electron beam. But here we have, technology has evolved. Electron gets fired one by one, and so you see a buildup of that pattern over time. I think these things last like 20 minutes or I don't know what, and then they film, they take a picture from time to time, and that's what you see in the middle there. You see that buildup of a pattern when only like 100 or 10 electrons are fired, and then fire 100 and 200 and 500 and 2000 at the bottom there, and then you see these patterns emerging. So that should be clear. So let's go back to the left hand side. We open the slit fully, of course, then even more electrons get through, and we see a much pattern that's much more clear. A lot more intensity of the light, I would say, but it's actually just a distribution of electrons, and then you open the 2 slits, and you see it's even more electrons get through. It looks very bright now, and we clearly see that there's an interference pattern in the middle there, and then the mask moves more and more to the right, and then the left hand slit gets covered, so we're back into another pattern that slowly gets less and less bright, until we close the two slits again fully by moving the mask as far as we can to the right hand side, so both slits are covered. Now the interesting thing for me about this thing is that all these papers, they write about the interference pattern of the electron when the two slits are open. And we have this magic then that says there's two possibilities here. The electron goes through one or two. I mean, there's two paths here, okay? Quantum mechanically, two like events that can happen, and we associate an amplitude, probability amplitude, with each of these paths. It's sort of the path integral formulation of quantum mechanics, but you can also do it using the quantum math related to just a simple two-state system and stuff. But they focus really very much on, we have two slits and we have an interference pattern. Well, what I find very intriguing is there's no attention when you look at when one slit is only open. You do see on the right and at the top there, when the left slit is open, you also see like a secondary and tertiary and ternary, or I don't know what you call it, but you see second, third, fourth, fifth order diffraction patterns. The kind of, if you send light through one slit or a pinhole, you will get what is called an array disk, fringes and all that. So you get diffraction even when you send it through one slit or one pinhole. We have the same here, and these articles don't focus on that. It's going to be clear in a moment what I mean, but look at the top. You see sort of on the right hand side very faint bright spots, and then a bit black, and then of course in the center it's very bright, but on the fringes, on the sides, you also see a diffraction pattern even when one slit is open. So for me, the real mystery here is that needs to be explained is not so much these double slit experiments, but the single slit. Why is it that matter behaves like light when it goes through one slit only, and not only when it does, like when many particles go through one slit only, but just one by one. It's really like Mach-Zehnder interference, but for one photon at a time. It's exactly the same thing. What is happening there, and how do we sort of explain that? So mainstream theory, again, I hinted at that. It sort of says like, yeah, we have the electron gun, and these electrons go through the slits, one electron through one slit or through both slits at a time somehow. We don't know. We can't observe that. That's Schrodinger's. That's the box where Schrödinger put his cat in. And we have a detector on the other side. And so this is the big mystery. What we do know is that if we close one slit, we will have a probability distribution P1 there. And if we close slit 1, and then all the electrons have to go through slit 2, obviously, because slit 1 is closed, and we will have an intensity distribution, probability distribution as equal to P2. And yeah, when we open both slits, we have this interference pattern, really weird, which P12, and it's just to get that curve, we can't add the probabilities, no, because then we don't get that P12 curve. What we need to do is invent some kind of a wave function, a probability amplitude, and you see that phi1 and phi2, and we associate that with the path, and then depending on the length of the path, there will be some kind of phase difference when it arrives, or well, actually we don't know what that phase exactly is, but these amplitudes have a phase, and it's slightly different, and depending on the distance, the length of the path, and the position of the detector, or the length of the path from the electron gun to the detector will depend on the position of the detector, and so the phase will be different for the phi1 wave function than for the phi2 wave function, and so that difference in phase will then determine the intensity, which we calculate by just adding those two complex valued numbers, phi1 plus phi2, and then we take the absolute, because we will get a complex number. We take the absolute value, the magnitude of that complex number, and then we square it, and then we get a value for P12, the probability that an electron arrives at that position on the screen, which is given by x. So that's it. The funny thing here in this reasoning is, you've heard this 100 times, not more, 1,000 times. You looked at this experiment and you stare at it and you say like, yeah, fine, that's I don't understand it, but this is the quantum mechanical explanation. The thing is, it's wrong. P1 and P2, as he models them here, it's not what we see in reality when these experiments are actually being carried out, and they are now in the last few years. We have all these electron interference experiments, and they focus on, sort of the rough distribution, which actually does follow that P12 curve. But what we do see when one slit is open, and that's the figure 8.3, when one slit is open, we have secondary bumps, and we have a third order diffraction pattern and a fourth order. Of course, it depends on the width of the slit, how many bumps we have, but you can see that. Do you see that in figure 8.3? When one slit is open, it's not some kind of smooth normal distribution, centered around a mean with some standard deviation, and that describes then our normal distribution. The P1 curve, it doesn't look like the P1 curve in the diagram of Feynman. It looks like a diffraction. So we have diffraction when one slit is open, and then actually what happens is the interference pattern for two slits open very much looks like just a superposition of two diffraction patterns. Here we have one. This is an experiment that is performed in December 2000. Well, the paper was published in December 2018 in Japan by these guys are making waves now. You should download the paper too. An interference experiment with an asymmetric double slit. So we have two slits, and the nice thing about this experiment is that the two slits don't have the same width. One is larger than the other, and you can see 8.3. That's the one I showed already. It's a very thin slit, and we have a diffraction pattern there. Slit C3 is much wider. You see that on the right hand side there at the bottom. Just look at diagram C3. There we have pretty much that normal distribution, that the shape of that P1 and P2, like Feynman put it on his schematic diagram of what was then a thought experiment. So there we have indeed a big slit. It's wide open, a wide opening, and electrons go through, and most of them just go straight as to the center, but then it goes down left and right. But in 8.3 we have a much thinner slit, and there we get a diffraction pattern. And then the funny thing is in the middle, so we have a superposition of the two of 8.3 and C3, roughly speaking. But we do see, and that's the funny thing, and that's the thing that really needs to be examined, and I hope that's the thing that really needs to be explained. You see very, very tiny, it's called like Fraunhofer pattern. Fraunhofer pattern is in the spectral lines of a hydrogen atom. That was actually the first thing they discovered before they discovered actually the hydrogen spectrum, or while discovering it. It was that it was more absorption. You shine light on hydrogen, and sort of certain frequencies will get absorbed on hydrogen gas, and so the absorption of spectral lines is happening, and so certain lines just disappear. So that's where that gave rise then to the emission spectrum. When you have an absorption spectrum, you also have an emission spectrum. Of course, you excite the atoms, and they will radiate photons out rather than absorbing them. And that's the funny thing. So B3 is an interference pattern, all right, but you can see the interference is the main shape of that function B3 is really given by just the superposition of two very common diffraction patterns. The individual diffraction patterns for when, I would say, light goes through one slit. But here we're talking really about electrons going through a slit. So that's all very interesting because it's not what you've been taught. I'm sorry, in mainstream quantum mechanics, you don't talk about the electron interference experiments in this way in terms of adding just diffraction patterns. So to come back to this thing, I just put the two things nicely. One on the left we have an Airy disk. It's called an Airy disk from Airy was a British physicist scientist. Basically, again, these guys were pretty general. From white light. And white light going through an aperture, as they call it. I mean, think of a pinhole. Think of your camera. So light goes through it. If white light is a spectrum of light, of course, there's a lot of frequencies in there, slightly different range of frequencies. So, but this is midday light. It's called the D65 spectrum, but it's just basically midday white light from the sun. And you can see it's fascinating because the Airy pattern, indeed, you have fringes of very bright and less bright that alternate. But we also have different colors because the red light will diffract more than the blue because the average frequency is different than the average frequency of blue light. So well, there's all these things going on, and that stuff we can explain in terms of physical equations and electromagnetic waves being diffracted, and so we have our equations for that, but the patterns that build up that are there that we see are very intricate and very beautiful. So when we use a simple light from a red laser, well, simple idea, laser is not an easy apparatus, but it has one frequency only, and it makes it possible to produce what you see on the at the bottom there, red laser light through a 90 micrometer pinhole. See, light has a the frequency of the matter wave is much smaller, is much higher, and so the wavelength is much smaller than the frequency and of matter. So 90 micrometers. We're not talking nanotechnology here. That's why the wave character of light was discovered much earlier than that of matter. Yeah, these patterns are familiar to you. We have here a really nice one, nice setup. 27 orders of diffraction you can see. But on the right hand side there we have again this 2012 experiment, and I want you to look again not at the middle, where people are always looking at and what the paper writes about, but really at the more of the bottom thing and the top thing where only one slit is open, and where you do see yeah, we have a bright flat like a UFO, an unidentified flying object in the center. But we do have second, third, we have other orders of diffraction, at the left, at the top, where the left slit is open, and the same thing when the right-hand slit is open at the bottom. We have like the equivalent of an Airy disk for electrons going through one slit only. So yeah, I'm really too lengthy here. So, but here we put it all together. I have put Airy there. He has a nice head. So he was a 19th century guy who, his name Airy is the Airy disk. And so on the left hand side, what you have there is two pinholes, and we vary the distance between them. At the top, distance is larger than at the bottom, somewhere in between, and that really determines, if you have something like that, it shows this Airy disk does determine what we can see with normal light in a light microscope. It determines the resolution of an ordinary microscope because you have that diffraction pattern. And so on the right hand side again with the experiment and the buildup, but I said secondary, tertiary order, so it's really the same thing. The only difference is the scale. I said the frequencies involved in light and their wavelengths are different than for matter particles. Matter, the Planck-Einstein relationship tells us that the energy an electron because it's so massive. We're talking mega electron volts, while with photons you talk just electron volts, 4 or 5 electron volt. With an electron, it's 500,000, 511,000 electron volts. And if they get moving, we can produce electrons which have an energy of 200 mega electron volt. So it's much larger, and the higher energy due to the Planck-Einstein relationship tells us that the frequency gets much higher, so the wavelength becomes much smaller, and so we need much more. There's a reason why these experiments can only be carried out now. We live in exciting times, but we do see airy patterns actually when we do this, one slit experiments with photons, and if we do them with a lot of electrons or one electron at a time, it's the same thing. We get the pattern. So question really is then, what can we say about the wave for electrons, and what is its shape, and what kind of more classical theory could we offer instead of these amplitude waves? I'm showing this because I promised I would mention a few names of people that are trying to do what I say, instead of thinking in terms of amplitudes and wave functions, but they really think in terms of if we have some kind of wave, a complicated wave, and it goes through a slit or it goes through a pinhole, how will it shape change? And I'm showing here something that this is a very basic illustration from one of the very early articles of Frapponi, where he basically says, look, this is the idea. We have electrons being scattered, right, by a filter, or being diffracted by a slit and whatever. So if you have a plane wave, it will go through that thing, the pinhole or filter or slit, and the wave shape will obviously change. We'll have a cylindrical wave or a spherical wave. So we really need to look what we get from experiment, what the interference or diffraction pattern is, and now we need sort of based on that develop a sensible theory on how that wave, that electron wave, looks like. But in real terms, you see this thing is thinking about a wave that is really, some kind of oscillation in 3D space, and moving and hitting a wavefront. There's a wavefront hitting a screen, and so that's the whole idea. Because we do that for light. We have the Fresnel equations, and we have the Fraunhofer equations, and we know how it works for light. And we don't work there with amplitudes and quantum mechanical wave function. No, we just think it's an electromagnetic wave, and it's a complicated one, a special shape, and it's very difficult to analyze it because Maxwell's equations are not easy, and we have an electric field vector, magnetic one. We know together they describe the phenomenon. It's really not easy, but we don't work with quantum math to we know that light comes in photons, but we sort of have classical theory, but with the addition of the Planck-Einstein relation, the quantization of the energy, and we describe it, and with pretty classical theory. Not 19th century classical theory, but 20th century classical theory, I'd say. I don't know how I need to express this, but that's the idea. So now more history here is this is the 1921. I said 1921. You don't see Einstein on the picture here because the German scientists were excluded because of the First World War. So Einstein, sort of out of sympathy, that's the story, standard story. Apparently he had another invitation in the US. He was by that time a lot more famous. So Einstein is not on this picture, and there's a lot of German or Austrian scientists who are also not on this picture, and you will see them back on the next picture, which is a 1927 picture. But who is there is Maurice de Broglie. I spoke about him, and a lot of other brilliant scientists, and you see Hendrik Anton Lorentz in the middle there, but you'll see Rutherford there, and Millikan, and Madame Curie, who has 2 Nobel Prizes, one in chemistry and one in physics, and a lot of Michelson from Michelson-Morley experiment, and Bragg, and a lot of famous people there. But I'm just saying it that how lucky Louis de Broglie was to have a brother like that, and to have been, like, as a young guy with brain. Of course, you need brain, but he was there as a scientific secretary, and his brother was actually talking a lot about photoelectric effects and studying it. And the paper there, par Monsieur de Broglie, is a paper by Monsieur Maurice de Broglie. So, and you see the Planck-Einstein relation there, and he talks about already in 1921 about yeah, the photoelectric effect, and actually pretty much about what happens when photons hit electrons. And while Compton is not on this picture, I think, and he wasn't there, but they were aware of his work already. And they were talking about it. So let's move to the next one, the 1927. That's the most famous one. That's the watershed when, I would say, quantum mechanics won out, or was sort of became the theory, you know. So that's where Schroedinger, Dirac, and Pauli, and Born, and you see all these guys are in the picture somewhere. You can have fun with trying to identify them. You have 17 Nobel Prize winners there, and at the center again, Madame Curie, Hendrik Anton Lorentz, and Einstein, and I put a red circle around Louis de Broglie. You see, a young guy, but already, well, he's a bit like me. He doesn't have too much hair on the face, at least. And the next to him, you have Arthur Holly Compton, the very American-looking guy there. So yeah, they were chatting and talking, and that's. But at this conference, you know, you had Bohr and Heisenberg and Schrödinger and Dirac, and they were all presenting papers. And so the first paper actually on this new quantum theory was presented by Monsieur Louis de Broglie. And so I will talk about that, what he writes in there, and because that's basically, you know, the interpretation of quantum mechanics ever since 1927. You know, it's almost 100 years now. We're still working with these same equations, and I suggest that there's another interpretation possible of these equations. You will say, come on, they would have discovered it. I don't know. The fact that you're listening, if you're still listening to this presentation, actually means that you know there's something wrong with quantum mechanics in terms of how it explains things. I would say quantum mechanics, it's not wrong. Mainstream theory, no, of course it's not wrong. It's been tested and this and that. But it doesn't explain, you know, like I said, these interference patterns that we see in real life experiments when doing electron interference experiments. And it also is not very satisfactory in terms of, you know, we describe stuff, we use these amplitudes, but we don't know what they are. So there's no like mechanism. And of course, Heisenberg's interpretation is there is no mechanism, but frankly, Heisenberg, he evolved, and I'm not sure, you know, of course, they want to attract attention, but in the beginning, Heisenberg was a bit the same, you know, when these theories came out, and I still think it's the case. He basically said, you know, we're measuring the smallest of smallest things with the smallest of smallest things, you know, photons are little things, and electrons are little things. So we measure the sort of the shape and size and the properties of an electron by photons, and so these things interfere with each other, of course. So we can never really know what is what. And so he first called uncertainty Ungenauigkeit, which is a German word which basically means, you know, there's an imprecision there, a fuzziness, but it's really linked to, you know, the way reality is in terms of, you know, small stuff interacts with small stuff, and so that interaction between the subject and the object is not, you know, some mental observer, some consciousness that suddenly by some magic has an interaction with physical reality. No, it's just little stuff interacting with little stuff. So he called it Ungenauigkeit, and so it's only later that uncertainty acquired that sort of metaphysical quality, I would say, that you know, same metaphysical quality of the wave function, where we don't know what is the real and imaginary part that's oscillating, but what is oscillating was the physical dimension of these fields, because it's oscillating some kind of field, right? A quantum mechanical field, but it behaves like, you know, electric or magnetic field. It's just we don't attach a physical dimension to it. So that's 1927. So that's the first page of his La Nouvelle Dynamique des Quanta, the new quantum mechanics in English. And so the the relation he jotted down there, we starts with is just a very classical wave function. So we have u some I mean he looks at this here pretty much as a real valued function in 2 or 3 dimension, I don't know, but it looks like a scalar function, right? And it could be anything, and he also says it could be anything, but it is a function clearly of x, y, and z, 3D space coordinates, and t. And so if we think that wave function describes a particle, yeah, it will be a function of x, y, and z. We think the particle is somewhere in space, right? And it's somewhere in space at some point in time, t, right? So it's a function of x, y, z, and t. And the zero subscript there, that's funny. You might think, well, where's the subscript? Why is that there? It really refers to the stationary frame of reference. In its own frame of reference, x, y, and z is 0, 0, 0. I'm here, right? I'm the origin of my reference frame, and t is, it's my time. It's yeah, it's proper time. So of course, wave functions, we want to work with that, and we want to, superpose wave functions and do a lot of stuff with them. So there's certain mathematical conditions that correspond also to, sensible assumptions about reality, which basically we're going to ask. That's a pretty well-behaved function. We have 4 variables there, and these 4 variables are, length, space coordinates, and time through special relativity theory, of course, not Galilean relativity, but even in special relativity, we can separate. If this thing is sort of a normal mathematical function, we can separate it out in 2 functions, the product of 2 functions. One is a function of space only. The electron is here, and then much later it's there, but it's a function of space and a function of time. And the function of time there is written as really the oscillation as a function of time, as a cosine function. Cosine function of what? An argument that is a phase, and so it's 2 pi times frequency. So that's an angular frequency, 2 pi's nu 0, the v, well, it's not a v, it's a nu for frequency. I could put 2 pi f actually, and that's much clearer, but these are the symbols that the Broglie used, times t. So that cosine function goes up and down. We fix a point in space, x, y, z. We say our particle is there at this moment, and so if the particle stays there, then f, x, y, z will not change. We fix it in space, sorry, and then but the time part of our wave function will oscillate, and so the magnitude of the whole wave function will go up and down. So that's pretty standard theory. I should not be explaining this, but I want to do that to make sure that we go nice and slow. So here you have that actually. We have a very simple example of something that oscillates in 1 dimension. It's not like a water wave here. Don't think of that. The water is not like a water molecule that really goes up and down in space, or a sound wave, where you think of an oxygen, or well, whatever molecules there are in the air, moving up and down, or side or laterally, or depending if you think it's transverse wave or a longitudinal wave. But something is oscillating clearly, and it's a stationary wave. The wave function of the Broglie was an equation for a standing or stationary wave. And I like this animation because it comes from Wikipedia, of course. Oh, well, maybe not actually. This comes from another website. I don't know. You can see you can model the red stationary wave. The wave stays on the same spot by the sum of 2 waves that move in opposite directions. Actually, the blue and the green one, they move in opposite directions. So we have 2 component waves, and they move in opposite directions, and they make up that red wave, whose amplitude at some point in space, a specific point in space, varies with time. So this is really, it's a stationary wave, it's a standing wave, but the problem with this wave, of course, is that it's all over space, and if you want to have a standing or stationary wave for a particle, we know our particle, we need to localize it in space because the electron is somewhere, the atom is somewhere. So that's where we start then working with wave packets. That was the solution of the Broglie, because he realized that, yeah, this wave equation for a standing or stationary wave it doesn't work because it can't represent a particle because it's everywhere. And so if it's everywhere, it's nowhere really, and then we can't even use the concept of a particle because the idea of a particle, implies that it must be somewhere in space, maybe not at a specific point, but at least some area in space, a small area in space. And so that's where the Broglie then realized, okay, what's the solution here? What's the way forward? If I want to make a wave function for an elementary particle, I need to make a wave packet. That's the only way how I can sort of build a wave packet, that travels then or stays on the same spot in space. But I'm gonna add a lot of these standing stationary waves, and with slightly different frequencies, so slightly different wavelengths also, and maybe different velocities. I'll just gonna add them, so then I have a nice wave packet. And I'll show you the inconsistencies of this reasoning in a moment, because it's the main inconsistency really is, I mean, there's a number of them. I write about them in my papers, but the main one is really that you get a dissipating wave packet out of, you will be using standard equations to model the wave components, because you think, well, we're talking some kind of physical wave maybe, and so we need the physical equations in physics. And you're gonna have a wave packet, all right, but it's just gonna stay together like for a very brief instant in time only, and then it's gonna dissipate away. And well, I'll talk about it in a moment. So let me move on. So the Broglie then goes on in his paper, and what I'm putting there is a Schrodinger's equation, actually, which models, as you know, an electron, but in a specific setup as it orbits around a nucleus. And you will say you're using, the precise language there. An electron does not really orbit around a nucleus, but then it does and it doesn't. You can talk about energy states, finite or definite energy states, and they describe an electron orbital, and you can use all kinds of language that you want, but in the end you will model, you will get a wave function out of some wave equation. And that wave function you see on the right hand side there will indeed, be nicely split up, or you can split it up between a component that varies in time, the complex exponential there, E, Euler's number, and the exponent is then, because of convention, minus the imaginary unit divided by AH times the energy and the time, whatever unit you use for to measure time. And then you will have another part of the wave function. I mean, this comes from Feynman. He uses the same phi as a function of, our three-dimensional position vector R, but actually, it's a different phi, because the first phi, which is a function of three-dimensional of the position vector R and T, and the phi of three-dimensional space only, that's sort of we have like an envelope function of the part that varies in time. So you should play with these things, and you have played with these things, and you know how that behaves mathematically. You just don't really know what is the physical dimension of that real and imaginary part of that wave function. Is it like what's the physical dimension? Is it Tesla? Is it Coulomb per meter? Is it what? There's no physical dimension there, and we would very much like to. I mean, if we can't give it a physical dimension, we can't sort of say what it is really. What is oscillating in space? So we'll try to do that. On the top there, you have that animation again from Kiridi, which sort of models a wave packet. That's the second fundamental problem with using wave packets. Actually, we sort of think, we have one wave packet, but you need to limit the domain of your component waves to get only one wave packet, because if you don't lead your domain, you still get a wave that's all over space. You see there, I have my wave is all over, but I can clearly see bumps, lumps, and as you can see, there's a green dot there, which measures the group velocity. My lumps, my wave lumps. I have two green dots, one at the beginning of a lump and one at the end of a lump. And so as you see, the green dot is the group velocity, and it's slower than the phase velocity, because that's the red little square or red dot, depending on the resolution of your screen. the phase velocity is faster. But so that's a component wave then, and so we'll have a lot of these. And well, it's a component wave. It's actually a wave made of several waves. And on the right, you have a formula which we'll know, which you should know. The group velocity will be, you know, the derivative. The derivative of the frequency, angular frequency, with respect to the wave number k. And what's the wave number k? If I need to remind you, I have it on the other side. K is it's like the wavelength in space. So well, the wavelength in space, but expressed in radians. So it's 2p divided by the lambda, the wavelength. But so wave number is like a wavelength expressed in radians. And we also have a phase velocity. Phase velocity is always easier. Phase velocity is well, a phase velocity actually we can we need to determine wave by wave. So we just have well, we can also determine it for the group, for the wave that's made out of components, but it's just the frequency divided by the wave number. And so yeah, then we have really on the light on the top right, left corner, just, you know, the definition formula for angular frequency. You know, you see frequency, angular frequency, and cycle time t. They're all related to by 2 pi, the formula for a circle. So we said that the logic in that 1927 paper, which you can go through, you can download it from the library of the Free University of Brussels. They're all there. Unfortunately, it's in French. I have not come across I mean, a lot of these papers are translated in English, but a consistent translation in English of all the papers and the discussions, because the discussions on the papers is very interesting between all these big guys questioning each other on what makes sense and what doesn't make sense. I have a paper actually where I translate some, you know, remarks of Rutherford and Lawrence, and it's interesting to download those papers and see the original in French, because a lot of the it's another digression here, but a lot of the folklore, I would say, or the stories that are being told about these conferences, like Einstein telling Bohr that, you know, and having heated discussions and you know, having talk about, you know, this thought experiment and that thought experiment, and then Einstein saying, you know, well, you know, God doesn't play dice, and Heisenberg then saying, like, you know, stop telling God what to do. You don't see that kind of stuff in those papers. It's not there. Einstein is actually, you know, asking a few very intelligent questions. And basically, you know, the way I read these things is actually that he doesn't believe that this quantum mechanical stuff it makes sense, but there is something wrong with it, right? And that's what Einstein feels, but he expresses it much more politely and in a sharp way and in a very gentle way than, you know, these so-called heated discussions that go nowhere. You know, when I read some of it, I think Einstein, and that's sort of clear from his biographies, also from the biographies that have been written about him. He didn't write his own biography, but from his correspondence with people like Ehrenfeld, for instance, who committed suicide, that he's basically tired of it, and so he lets these young guys run with it, Schrödinger and Dirac and Heisenberg, and say, like, okay, fine, I'll see where you get. So de Broglie, back to him then. But just to say that, you know, the standard story you get in your physics course is surely not. Look at it again, I would say. So the Louis de Broglie, that's what we said. He thinks of a particle as a wave packet, right? And it's composed of component waves, elementary waves, or whatever you want to call them, that have slightly different frequencies, f or nu. So we have a subscript I there. The I is not the imaginary unit there, but it's I is 1, 2, 3, and then we don't know. Also, that's the other thing in quantum mainstream theory. So should we think of this wave packet being composed of an infinite number of waves or a finite number of waves? It's not an innocent question, because of course the Planck-Einstein relationship tells us that, you know, a wave will carry some energy. Well, in general, wave theory tells us a wave will carry some energy, an oscillation carries energy. So if we have an infinite number of component waves, then each of these waves has zero energy, while if we think of it as a finite number of waves, each of these waves will have a very small but non-zero amount of energy. So these questions are all unanswered in the standard quantum mechanical argument. And now we have this funny distinction between the group and the phase velocity, and we know the group velocity needs to correspond to the classical velocity of the particle, but I said that wave packet will dissipate. So the concept of group velocity becomes, yeah, okay, fine, at some specific point in space and in time, we can sort of imagine a group velocity and calculate it, but and then we'll say, okay, this is the speed of the electron. But if the wave packet dissipates, goes away, and we know the electron in reality does not go away. I mean, does not dissipate. It's there, it's somewhere, and it just doesn't fall apart. It doesn't disintegrate. So we have a lot of stuff there that just doesn't make sense. And you can read what is there. We know the phase or the frequencies. There's a bit of a bad language there. The frequencies nu I, it's not the phase frequencies. Well, I could call it the phase frequencies because these are the frequencies of the component waves, and and each of these component waves will have a very precise phase, unlike the wave packet. So they're related to wavelengths. Also with the subscript I, going from 1 to, well, infinity, n, we don't know, infinite number or a finite number of component waves. And we'll model that by a dispersion relationship, which it's called a dispersion relationship because mostly if we don't have you need to have a special type of relation between the frequencies and the wave numbers to make sure our wave packet stays together. And in quantum mechanics, it doesn't stay together. Why? Because, well, we will use the Planck-Einstein relationship, and it sort of falls apart really because the I'll show you. Yeah, the wave packets have a rather nasty property. They dissipate away, and a real live electron does not. And this is where I want to quote is. You have these very intelligent people, and the banquet with the King of Sweden in 1933, when the professor or the chairman of the Nobel Committee Prize for Physics sort of tries to translate all these equations from the Broglie and Schrödinger and Dirac and Heisenberg, and he says this to the King of Sweden, or the whole crowd that is there, and celebrating the award of the 1932 Nobel Prize for Heisenberg and the 1933 Nobel Prize for Schrödinger and Dirac. There was a bit of a postponement, so they were actually awarded together in 1933. And he says this matter. So he gives an introduction about these waves that I just talked about, and he said, so we have these kind of waves, and matter is formed or represented already there in the language. You think like, okay, so what is it? Is it formed or is it represented? Here sort of he stays vague and says like, well, I'm not going to say matter are these waves. No, we represent them by waves, but so matter is formed or represented by a great number, again, infinite, I don't know, but of this kind of waves, which, and of course he understands that they have somewhat different velocities of propagation. I said they have different phase velocities, these component waves, and they have a phase, but they combine to represent our matter particle at the point in question. You know, at some point in time, and some point in space, we have this representation of a matter particle. Okay, and so he goes on and says that such a system of waves forms a crest. That's the wave packet, which propagates itself with quite a different velocity from that of its component waves, and this velocity is then the group velocity. And so it's you know that a group velocity is a classical velocity. It's 10% of light speed or much slower, or and then these phase velocities, that will be superluminal velocities, and people say, yeah, that's not consistent with relativity theory, but then they go like, well, it's a phase velocity, so it's not a signal and you can't use it, one of these component waves, to transmit a signal. But it's really very, I found it really very funny when I read this stuff. And then so he goes on, such a wave crest, or the wave packet, represents a material point. So it represents a particle, which is thus either formed by it or connected with it. And again, you have that very vague and fuzzy and I wouldn't call it philosophical. I just call it plain unlogical language, imprecise. And it's called a wave packet. Okay, so material point which is formed by or connected with these waves, and it's called a wave packet. So then he goes on and says this, and as a result of this theory, one is forced to the conclusion to conceive of matter as not being durable, or that it can have some definite extension in space. Wow, I have a page. I mean, my book is called The Emperor Has No Clothes, because I feel like a kid standing in a crowd and cheering on the Emperor because he wears the finest clothes, but he actually got tricked into paying a lot for nothing, and he walks around naked. But because he's the Emperor and this and that, no one dares to shout like, "Hey, you actually don't have any clothes on, you're naked." So I feel like a bit the same, because this sort of, for me, does not make sense. Let's continue with reading what he wrote. He said the waves which form the matter. So here's a bit more precise. He says the waves not which are connected or represent the matter. No, he says these waves form the matter, and they travel in fact with different velocities and must therefore sooner or later separate. So that's the dispersion problem that I talked about. So he says matter changes form and extent in space. So the picture which has been created, the picture we have since ever, I mean, since I was a kid, but also like which mankind has of the idea of matter itself, the meaning of the word matter. He says we should change that picture of matter being composed of unchangeable particles. The picture which has been created of matter being composed of unchangeable particles must be modified. No, I agree. We need, I mean, these photoelectric effect and all that, and photon electron interference. Of course, we need a different picture of matter particles, but this language here, and what he says is that matter changes form and extent in space. Well, it may do so a little bit. I mean, if it's sort of like a wavicle going through like one slit or two slits, we know that it may interact, and we have a wave shape there, and interaction between waves and all that. But at the other side of when it goes through the slit, or it's an electron, and either it goes through the slit or it doesn't, or maybe it goes through the two slits, we don't know. But at the other end, if it goes through one or two slits, it will be absorbed, it will hit a detector screen, it will arrive as a lump of energy, or a wave lump, or whatever lump, but it's there. The electron is there, and has a quantized amount of energy, and it has a mass which combines its rest mass and then maybe the energy it has from its motion. But it's not dissipating, for sure not. Real life electrons, real life particles, or wavicles, whatever you want to call them, but real life matter stuff that we use in these experiments doesn't dissipate. So it may change form and extend in space a little bit, I said right there, when we force it through a slit or two slits, or when it doesn't go through and it gets absorbed into the material of which this latest our screen is made of, but not really fundamentally so. So we have it's hugely. I mean, for me, it's philosophical. I've got a few degrees, but one of them is in philosophy, and for me, this doesn't make sense. So let us review the Broglie's logic once again. If we're going to be working with these wave packets, if we're going to consider a wave packet as what I write here as a potentially, or as a, not potentially, but really like as a truthful, and I'm going to call it a representation of the matter particle. And don't ask, what do you mean with a representation? Is it real? Is it real? Is it in your mind? No, but you know what I mean. We're talking, you and me, we're trying to create meaning. And so we have a wave packet there, right? And we to get that wave packet, we use the Planck-Einstein relationship. That's the one we get out of experiments, and that explains black body radiation and whatever. It sort of tells us that basically, the energy in an oscillation will be equal to, it will be proportional to the frequency, and the proportionality constant is Planck's quantum of action. E is h times f. So we must have, a number of waves, and they must have slightly different energies. And so we must have, and we must then divide that energy also somehow of the whole wave packet over these component waves. So that's what we're doing there. We don't have a precise idea anymore of the energy of our particle. We just have, indeed, we need the uncertainty principle here. But we need it because we have that wave packet concept or representation. And so, yeah, well, that's the only solution, the only way out. And also sort of to localize, again, that wave packet, we need to limit its domain, because if our wave is oscillating the wave all over space, then we'll have infinite energy as well. And so, yeah, so we limit the domain, and we sort of say, like, our particle, we don't know where it is, but it's going to be like in this space, more or less, between potential wars or barriers, or a potential well or whatever. And then we have some Ungenauigkeit, as said. I'm using here the original German words because uncertainty is a word that we use it and we don't know what it means. It's an Ungenauigkeit, is sort of a fuzziness, or Ungewissheit, maybe we don't know. I think Ungenauigkeit and Ungewissheit, these were the two words which Heisenberg was oscillating between. Ungenauigkeit is really something in nature. We measure stuff with the smallest of stuff, and so there's always going to be some imprecision that is actually linked to the lack of precision of our measurement apparatus, because it's like trying to two blind people who are trying to touch each other and trying to determine how each other's face look. So that's gonna not be very precise because they don't see. They only have their hands, and these hands will be pretty precise, but both of them will get an image of the other person, but it's not going to be a very precise image. So that's Ungenauigkeit. That's something that's in nature, and Ungewissheit is more it's inside our head. We just don't know why, because we can't see. It's the box of Schrödinger, and he put his cat in there, and this cruel radioactive apparatus that releases poison. So we have agreed that we wouldn't open the box now or whenever we want. We're just gonna look, every 10 seconds, or maybe at the end or after an hour, and depending on what we agreed on, and the how fast we want this cat to die. We open the box or we don't open the box. So that's an Ungewissheit that we introduce. It's our decision. We don't know, or we don't want to know. And so these are two very different concepts. And uncertainty sort of in mainstream quantum mechanics mixes both. So I'm just saying here, mathematically, logically, we can't have a wave packet if we don't introduce that thing, indeed, where we say, there's this uncertainty in the energy. And if it's Ungenauigkeit or Ungewissheit, we don't know the energy value, or in reality, energy is some kind of fuzzy thing in nature. The bottom line is this, though, that we do time at the same time. We assume there's a very precise relation between the frequencies and the wavelength, and that's something for me as we're looking from I don't know, physicists hate philosophers, but here we suddenly get out of this uncertainty, and we say, like, well, we don't know what we don't have an exact value for the energy or for the momentum. It can be a range of values, but we do assume that there's a very precise relationship between the frequencies and the wavelengths of these component waves, and that's sort of like, bam, exact on. The frequency of wave component wave number 3 or 4 or 1, or set the F with the index there, I, that's going to be, you know, that wave is going to have a precise energy divided by h, and you start thinking, right, okay, fine, here we're with this problem. How many waves are we talking about? How do we divide the total energy over those component waves, etc., etc. And so we'll have a frequency for each component wave. We'll have a wavelength for each of these waves, and that's the Broglie relation. We'll have a de Broglie relation for, so lambda E is h divided by the momentum of the individual component wave pi. There also we need to sort of divide somehow the linear momentum of our electron over these imaginary or well, yeah, the component waves. And yeah, what happens then to our concept of velocity? Do we sort of break our concept of classical velocity v? Do we also break it down in you know, the thing is, you know, all of your concepts become like fuzzy, and you're like left with a theory where you say like, what is what, right? And even mass also becomes a fuzzy concept, because if there's uncertainty in the energy of our electron, it's somewhere there in space, right? We look at it and it's there. We say it's there, and what is it? Well, it's this wave packet. So to model this wave packet, we need to assume its energy is uncertain, but we just said the particle is there, right? It doesn't move, and so it has a rest mass. And we measure that rest mass very, very precisely in experiments, right? We know exactly how much, I mean, an electron, what its rest energy is. That's very precisely measured. But then we come out of this thing saying that, you know, the energy is uncertain, and so then I'm saying, going like, okay, fine. So there must be also then uncertainty in the rest mass of that particle. So, but then there isn't, right? Because we measure it and there's nothing that tells us, you know, this rest mass is not very precise. You know, we can do more and more precise measurements, but we do see in nature, reality, that a particle has a very precise energy and rest mass. So then here, I mean, also talking about this concept of classical velocity, the concept sort of breaks down, because we can rewrite the Broglie's relationship for a component wave lambda e as h divided by pi as a, you know, we substitute the mass for energy divided by c square. So h divided by m subscript I times the classical velocity is then hc squared divided by the energy times the wavelength. Then, so what happens to our concept of classical, that's the classical velocity of the wave packet v, but here we are writing it in terms of, you know, it's c squared divided by the velocity of our component wave vi. That's not new there. It's the frequency times a wavelength, so it's actually the vi is not new either in the last. V, the classical velocity of our particle, what I write there, is equal to c squared divided by the velocity of our component wave, and that's where the problem starts. Or I mean, it's another problem besides that philosophical problem of having uncertainty in the energy or the rest mass. Is this one also that the concept of classical velocity breaks down, because depending on the component wave we're looking at, we get a different classical velocity. So we only can, but we do think of a particle as moving with some kind of velocity and constant velocity in space. But that velocity v can only be constant if the product of the frequency and the wavelength of each of these component waves, so that's the velocity of our component waves, is the same for each component wave. So, but that's not consistent with our first assumption, where we said, you know, we need slightly different frequencies and slightly different wavelengths, and so it all breaks down. It's just like we don't know what was what anymore in the Broglie's paper. And in all subsequent papers, we just sort of leave it out there in the open, and we're with 2020 now, and we're still discussing these things. And so that's where I think I have a theory with better answers. still some questions left, but the other thing really is, I mean, that's the third thing, and then there's many other inconsistencies also when you start looking at wave equations. You know, wave equations model the properties of a medium. I would say the medium of space-time here, the ether or whatever you want to call it. And that's I go more into detail in papers on that. But the other thing here really is these superluminal phase velocities, because yeah, the velocity of our component wave, depending on the energy value, will not be equal to, it will be less than c. So we have c squared divided by well, it's actually the velocity of our component wave here. Sorry, we bring the v to the other side, so vi, v with the subscript, I will be equal to, you know, c squared divided by our classical velocity. So the phase, the velocity of the component waves will be superluminal. It will be what I put there, vi is equal to c squared divided by v, so that's c divided by beta, the relative velocity, and that will always be bigger than c, because beta is a number that varies, that is larger than or equal to 0, but it's smaller than 1. And we have a superluminal phase velocity, you know, and then you go like, okay, that's not possible because of relativity. Special relativity this is an absolute limit to any velocity in whatever frame of reference you are, you know, stationary or moving or accelerating or whatever. Nothing goes faster than light. And well, then people sort of blubber around and saying, well, you know, but this component wave is not really like a signal, and it's really like a signal that cannot travel faster than light, and so that wave packet as a whole, that will be a classical velocity, and that will never be faster than light. But I'm going like, you know, we do have component waves, and then you know, if they travel faster than light, so that's not possible. So these component waves cannot really exist because they contradict relativity theory. It's problem after problem after problem. And these problems occur because we choose to represent a particle by a wave packet rather than a single wave. So that's the bottom line, and you will say that, yeah, but you know, sure, de Broglie and Einstein will have thought about it, and all these smart people, like, you know, you just said it yourself, it can't be a single wave because then we can't, you know, localize it in space. And so there's a lot of reasons why you want a wave packet. But the thing I'm going to say here and I'm going to show is that actually we can model an electron or any matter particle by a single wave only. We just need to move away from this idea that it needs to be a linear wave. We just need to think more generally that, you know, a matter particle, yes, it's some kind of oscillation, but it's not necessarily an oscillation that is linear. Well, and it is and it isn't. I'll show you in a moment what I'm thinking of. So this is the alternative modeling of a matter particle, and you will say this is crackpot theory and whatever, but it actually is not, because this Zitterbewegung theory. Zitterbewegung is a word that was coined by Schrödinger because he had his wave equation. It's kind of funny that he got his wave equation first for electron orbitals, which are actually much more complex to model, I would think, than, you know, an electron in free space. But his equation came first in 1923, and then Dirac modeled a more general wave equation for electrons moving in free space. So when there is no positive nucleus or, you know, Coulomb field to hold an electron in close to it, and you know, localize it in a small space, the space that is determined by the size of an atom or a molecule. So Dirac formulated this very general equation of motion, as he called it, for an electron. And Schrödinger immediately saw there's a very trivial solution for this thing, but he didn't quite understand it. Both Schrödinger and, I mean, Dirac basically, because Dirac did the speeches at this 1933 Nobel Prize Award. And he spoke for both Schrödinger. I think Schrödinger was actually not present there because he had just moved to Ireland. So Dirac talks about it very prominently in his acceptance speech when he gets his Nobel Prize in the same speech from which I quoted the chairman. He talks about this Zitterbewegung that Schrödinger discovered, and he said, you know, this is really funny. My wave equation, for which I get this Nobel Prize here, there's a very trivial solution for it, and Schrödinger found it almost immediately, and it's really, you know, a charge, and he called it, that's the thing where he made a mistake. He said it's an electron moving around locally in a Zitterbewegung, a very fast oscillatory motion, speed of light. That's actually mathematically what came out of it. But of course, the electron itself has a rest mass, so it can't move around at the speed of light. So we had this inconsistency, and so Schrödinger and Dirac didn't make like the next step saying like maybe what is an electron anyway? Maybe an electron is like a point-like charge, you know, zittering around locally, very locally, and that's what I'm doing here, and that's actually what I'm doing. I mean, there's a whole history, of course. I mean, the ring current model of an electron is quite old, goes back to 1905, and then David Heston has revived this Zitterbewegung theory all on his own in the 1980s, and so there's a lot of researchers working on it. And the sort of what I'm telling here is for them very basic. We're gonna make a model of an electron. That's the other thing in mainstream quantum mechanics. You think of an electron as a point-like particle, and then you just don't ask any questions, and then you get in all these weird logic of, you know, where is the charge, and but you don't you give funny answers to that. Here we are just saying like, you know, we have this trivial solution out of Dirac's equation for an electron in free space, so we may imagine an idea of a, yeah, it really is very smaller than within the electron. We have like a point-like charge, and you can see that on the right-hand side. It orbits around. It goes round and round and round, and that motion, I mean, it's not necessarily perfectly circular or, you know, elliptical or some precise mathematical shape, but it does go round and round, and there's an irregularity and sorry, a regularity in it, and the motion may be chaotic, but we because it's so fast and we can't measure it anyway, you know, the wavelength as and the frequencies involved. I mean, Planck-Einstein relationship tells us that frequencies are just amazing. I mean, we can't imagine such small lengths and such high frequencies. So that's what Dirac also said. We can't really check this model, but there's, I mean, now we can do a lot more. But this is really the idea that matter particles, yes, they should be modeled by an oscillation, and this Zitterbewegung theory, or you know, Schrödinger's trivial solution is recognize that, you know, modeling these matter particles as a linear oscillation, as a wave packet, it just doesn't do the trick. We get in trouble. And so what does do the trick then is, well, some circular motion, I would say. You'll say circular motion is not an oscillation, but it actually is. You know, if you have a sine and you add a cosine to it, you get something that goes round and round, right? So we have cosine of phi plus sinus of phi, and we add these. You know, the sine is the vertical thing and the cosine is the horizontal thing, so we think of them as like some kind of directional or vector thing. We can add them, and the phi, the argument of the sine and the cosine, you know, varies with time. The phase is equal to, you know, the angular frequency of that motion, and time. Phi is omega times t. So you have that green circle there, and we think of that tiny point-like charge going around and around, and the radius of that orbital motion is the radius of our electron. Well, the radius of our Compton. In a Compton experiment, the effective radius will be the radius of that effective area of interference. We fire photons at some point small, I mean, some area in space, and what emerges is that the electron is, yeah, occupying a space like a surface. We can measure that surface, the surface of interference, and that's going to be equal to that Compton radius, which we have at the on the left hand side there. Sorry, right hand side, A. And the Compton radius A, it's equal to h bar, the reduced Planck constant, divided by mc. And so how do we get that out of our equations? Really fundamental equations in physics, the very fundamental ones, not sort of uncertainty principle or things you can't put your finger on really, but these is, the energy mass equivalence relationship comes out of the depth of relativity theory, and has been shown to be, would say, true, but you will never know truth, of course, but it hasn't been falsified, would Popper say. And then we have the Planck-Einstein relationship, which explains also so many things and hasn't been falsified yet. So if it's the same energy, yeah, of course it must be, we're talking the same electron, right? We're talking some particle which has an energy. Potential, kinetic, whatever, because we get mc square is h bar times an angular frequency. We could say mc square is h, not reduced, times the frequency, but then putting in the 2 pi again, we have h bar and angular frequency. So then, what is that angular frequency? And what is c, the speed of light here in this equation? Well, we think of the speed of light as a tangential velocity, as really the velocity of that point-like charge, much smaller than the Compton radius. It's really, and that's another argument. I'm not going to go into detail on that. There's something like the anomalous magnetic moment in that has been measured very precisely, and also involves the fine structure constant, again a sort of a scaling constant. So out of the anomaly in the magnetic moment, because if it would really be like a point-like charge with 0 dimension, just a charge going around, then the magnetic moment would be well, I would say the gyromagnetic ratio, because we need to make some assumptions about the angular momentum of that charge as it moves around at the speed of c. It acquires relativistic mass and all that. These formulas are a little bit more complicated than these easy illustration sort of suggest, but you can do a lot of calculations and for that, and that's with these forces, and then the idea of momentum. Relativistic momentum, and what you get out of it is that the G ratio for this kind of theoretical electron would be 2, which explains why it's a spin 1-2 particle, because that's the other way around. But we have, it's not exactly 2. So actually that point-like charge, that green dot there on which the force is acting, that centripetal force that keeps it in its orbital motion, is very much point-like, but it has a non-zero dimension. But that's something else. Here I just want you to think of the basics of the model, which do not which just to think of, that green dot is small enough to be thought of as something point-like in this model, and then it will have a tangential velocity, and it will be given by the radius of that orbital motion, so that's what I put there. C is a, that radius, times the angular frequency. So that gives then an interpretation of that mc square as h bar times omega, because I interpret both c on the left and on the right, omega in terms of this orbital motion. C is a tangential velocity, and omega is an angular frequency. So then I can write the frequency, of course, as c divided by a, 2 scalar quantities. I do the substitution. So we have a formula for energy on the right, m times a square times omega square. I'm saying it's an energy formula, right? Because energy will always be equal to will be proportional to the square of the amplitude of an oscillation, which is a, the radius. That's the amplitude of this oscillation. Think of it going up and down and sideways simultaneously. It's a 2-dimensional oscillation. So and then it will be the energy of that oscillation will be proportional to the frequency, the angular frequency, and then we have a proportionality coefficient in such a, if we would be talking one oscillator only and non-relativistic speeds, the constant of proportionality would be 1/2, so 0.5. The energy, and you have seen that a classical harmonic oscillator is 1/2 times the square of the amplitude times the square of the angular frequencies. But so here we have a 2-dimensional. So classically, you can think, and it's actually pretty much correct, actually. If it would be a classical, if velocities would not be relativistic, then we would have 2 times 1/2 times ma square omega square, and we would have ma square. But here we do have light speed,
And the funny thing is, I mean, that's what I write about, and I show that in my papers. We can do these calculations with the force, you know, force in the x direction and the y direction, and centripetal force, and this and that, and we arrive at the idea of an effective mass of that point-like charge, and we can show this is relativistically it works as well. But the point here is we have that ma square, omega square is equal to h bar times omega, and you know, then we do the substitutions again from the third formula. A is c divided by the frequency. So frequency, and then we move stuff to the other side, and we get, I would say what we want to get, but no, we just get what we get at Compton radius. H is H divided by MC. So it's funny, Compton radius actually was a word I you know, when I did my first blogs and all that, and I saw that, you know, traffic was picking up a little bit, I Googled my name and I saw that it was associated with the Compton radius, and I thought like, whoa, pretty famous already. But I realized it was because everybody talks about a Compton wavelength, and nobody, I mean, I'm apparently the first one who sort of thinks like, you know, Compton wavelength is a circumference rather than a linear wavelength. And so if you talk about a circumference, a circular length, then we have a Compton radius. So that's the one we get here. I said I would very briefly show you, you know, how the two-dimensional oscillation. The original idea, and you may laugh about that, is I was talking to my son on, you know, I love motorbikes, and he's studying engineering, and you know, we did a few motorbike trips together on street bikes and heavier bikes, and you know, quite a lot of bikes. I haven't ridden Ducatis and Harley Davidsons, but other bikes. But we were talking about, you know, the engines, and so at some point in time he was, as part of engineering, they think a lot about efficiency and vibrations and this and that. And so I told him that you know, motorbikes, I don't know if it's still the case, but the speed record was at some point set by a Ducati Monster engine, 796cc. That's the engine you see there. And you know, depending on your sense of aesthetics, it looks nice, it doesn't look nice, but at that point in time, it was the fastest motorbike in the world, or at least, you know, tested on track and certified as being the fastest one. Yeah, top speed's way above 200 kilometer an hour. And I told him like what makes this machine so this engine so nice and fast is that, you know, the two cylinders are set in a 90-degree angle. You can see that. I put a Harley Davidson on the other side engine, where the angle between the two pistons, the cylinders, is 45 degrees, and that has a number of other advantages. Basically, Harley Davidson engine is a lot more compact because of that angle. That's the main advantage of a Harley Davidson. It's a much more compact engine, because if you put the two cylinders in a 90-degree angle there, you need a lot more space for your engine, of course. You can see that it's sort of more bulky. You know, the second cylinder sort of sticks out, and how do you sort of put it between the underneath the fuel tank and this and that. The design got a lot better actually of Ducati. It's always been a nice machine, breathing speed, but I think the new Ducatis with the 90-degree angle, you know, managed to make it look a lot nicer. But a Harley Davidson there, 45 degrees, more compact. You know, you will notice also Harley Davidson makes a nice sound. A Ducati Monster, well, it doesn't make all that much noise actually. It's pretty silent. I mean, depends on the muffler, of course, also. But it's smooth. And why is it so smooth? Because the 90-degree angle really allows that there's no loss of energy there. And that's what I put on the top there. You can balance the weight of your pistons, and with you know, you know, a crankshaft that translate that linear motion of your pistons into, you know, a circular motion. The crankshaft rotates round and round, and you know that a crankshaft is the most crucial part of an engine, and must be very strong to sort of support these knocks, the hits, you know, if there's these explosions occurring, you know, at so many strokes per minute. But crankshaft, very delicate, but, you know, and balancing it is very important so that you have no vibrations there. And you know, if you put your cylinders in a 90-degree angle, you know, a V8 engine, because the image is actually a V8 engine of cars where you have a lot more space in the underneath the bonnet of a car, you will put them in a 90-degree angle or a 180-degree angle, because that allows you that's a boxer motor then, in 180-degree angles, but a multiple of 90 degrees rather than 45 degree, I mean, not a 45-degree angle. Why? Because you can really reduce the vibrations, because you balance out the asymmetry that you will have in your crankshaft, the weights that you put on there. You see that the counterweight that goes round and round and round, it's you can completely balance it with the weight of your cylinders. So the Ducati engine, one of the reasons it makes little noise is that the noise is regular, very regular, and because the engine is very regular and there's no vibrations and no irregularities, it's just, and you can rev it up. You know, you can go much higher in rotations per minute than you can do with a Harley Davidson, which gives this low. Yeah, you can't rev it up, because the machine will vibrate. A Harley Davidson, if you look at it, you know, the engine block vibrates a lot more than that of a Ducati, and it's nice. It looks classy and stylish and whatever, but a Harley Davidson is not a very efficient engine. That's just reality. But it makes a nice sound, and it's a classic. So, but so that's another way. That's where I started thinking about and a two-dimensional oscillation, sort of imagining somehow like, you know, a Ducati engine is so efficient actually that, you know, it is like a flywheel. You know, energy gets stored in flywheels. I mean, it was stored. You can store a lot of energy in a flywheel. You know, a very heavy flywheel, a lot of metal, heavy pieces, you know, concrete in it, and then you energy you translate it in rotational motion, so that you have a mechanical storage device for energy. And you could do that if you would have no friction. We don't do it in an engine, but theoretically, if you would close the valves and you would have no friction on the pistons, and you would have also no friction in the air, because the air heats up if it's compressed. But you know, think of two springs on a crankshaft instead of two pistons. You know, theoretically, it's like a metaphor. If there would be no frictional laws or heat laws or whatever, then it would be a perpetuum mobile, like yeah, the perfectly flying. I mean, the flywheel. With no friction, you could store energy in it. Then you have a sine and a cosine, and so the kinetic and potential energy that is stored in when the air is compressed, you know, it will want to revert to its equilibrium position, which is a much larger space. So the air will push on the piston, and then potential energy gets converted into kinetic energy, and then, you know, that goes into the other cylinder. The kinetic energy then gets converted into potential energy, because the other piston is going to compress air. And I mean, I'm too lengthy here, but these are the formulas again for the energy. The energy in one oscillator will be proportional, and I have a k here. That's not a wave number. It's just a constant of proportionality to the square of the amplitude of the oscillation and the frequency of the oscillation. And so you wonder then, what is the constant of proportionality? And so in a classical you know, combining two classical harmonic oscillators, so with velocities are not anywhere close to light speed, that will be the formula for one oscillator: 1/2 times the mass on the spring times a square and the frequency squared. And so if we have two of these, then we have ma square omega square. So I said, this is a metaphor. It's just a way to think about. I said the relativistically correct analysis, you just go to my papers and you will find that there. There's no tricks here. I mean, I can assure you. You know, papers are around for a few years now, and no one has ever pointed out a mistake in my model. Whoa, this is don't worry, it says I'm talking now 2 hours and 20 minutes. You can take a break. I won't. I'll go through it. This is like the slide that I showed in the very beginning of my presentation. A lot of material here, so let's take our time. The figure on the right hand side at the top there, the theta beweging trajectories for different electron speeds. We talked about that one at the very start. So let's do it again. and briefly say that we have the black ring, which has the biggest radius. So that's the our electron in at rest. So we think of the electron as a ring current. So a charge that goes round and round and round, and we have the Compton wavelength is the length, is the path or the trajectory of the point-like charge. And so when it comes back to the same point, it will have gone through over a distance that is equal to the Compton wavelength, and the cycle time. Time is the time it takes to get back to where it was, and after one cycle. And then we make this thing move. All right, we said, okay, fine, we're in a different reference frame now, or the electron is moving, so motion is relative. Either we move with respect to the electron, or the electron moves with respect to us. And let's say that the relative velocity is 43% of the velocity of light. So we have relative velocity 0.43. Now we're in that blue thing, right? So if we then look at a trajectory, we plot it in I said this is in 3D space, just standard 3D Cartesian space. Then it will be that blue or indigo. I think it's indigo, or is it? No, it's not indigo. It's another color. Magenta, I think. Yeah, it's magenta. Sorry, magenta. We get this Archimedes spiral, right? And then we can consider a third possibility, a much higher speed. So the speed is 0.86. Then we get the brownish thing. Why are these colors not clearly defined? And then the red thing, the red brown thing is sort of at speed, 0.98. But that's the shape of the trajectory for different electron speeds. If you make your screen a bit larger, you will see that Zitterbewegung trajectories for different electron speeds. That is not a graph I made; it's been made by these Italian researchers, and I can use it because I've been in touch with one of them, very friendly guy, and said, he checked the publisher and said it's fine, use it. And the thing I want to note here is that okay, this looks nice and is nice for presentation purposes, but of course, why would the plane of oscillation, look at that black ring current, why would it be so nicely perpendicular to the direction of motion? And you're perfectly right asking that question, because it doesn't have to be. I said that ring current, will cause a magnetic moment. So the benefit of this model, I mean, there's a lot of benefits, but one of them is that we really have a nice explanation for the magnetic moment of an electron. Is well, if it's gonna go, you send it through a magnetic field, it will line up, and that's what you see in the middle there. It will have an angular momentum, L, so I put that polar vector there, and also put the L, the green thing, and then the mu is the magnetic moment, and because the charge is negative for an electron, they have opposite directions, so mu points upwards, and L, and so this is sort of if the x and z direction, I could take the y and z direction, and x is then the direction of motion. But in any case, you see that if one direction is the direction of linear motion and the other direction, we use the other ones to model that circular motion. It doesn't need to be perpendicular. We could have something that and it looks really funny and very ugly, what I point there, but this could be maybe like how an electron really travels, or that point-like charge, I would say, really travels through Stern-Garlick apparatus, through a magnetic field. And you may say that that looks ugly, but if there's a penning trap where they measure the magnetic moment of an electron, and if you I don't know, it's a German university who has sort of a really nice illustration of all the motions within motions, or motions, superposed motions. The motion is very, very complicated of a point-like charge in electromagnetic fields. I mean, the kind of electromagnetic fields you use to do these experiments measuring the magnetic moment of an electron. Well, I should say of a particle. Funny thing is, actually, I mean, talking about that now, The magnetic moment of an electron, you can't measure it in a Stern-Garlick apparatus because the Coulomb forces are so much, and that it's actually it would crash straight into the magnet, your electron. And so you actually measure the magnetic moment of neutral particles, like potassium atoms, if you're yeah, or with silver atoms, they're a bit more expensive, but not so much. Price of silver is not so high. But that's what you use in a lab, neutral particles. The thing is valid though, that we should think of these matter particles as or atoms that you use. The charge, the overall charge is zero, of course, because we have a positive nucleus and the electrons balance and that positive they balance out. But yeah, inside you have currents because otherwise, where does the magnetic moment come from? The funny thing, and what I find funny, is that the same researchers I mentioned in the beginning, Herman Batlan in particular, at the University of Nebraska Lincoln, he wrote in 1997, and his letter goes back to earlier suggestions by physicists like Broglie, who was a French physicist in the 20s. Basically said like we can devise an apparatus that would be able to measure the magnetic moment of an electron, and yeah, do sort of like the Stern-Garlick equivalent of a Stern-Garlick experiment for electrons. But the reality is we measure the magnetic moment in these penning traps, but we have not done a classical, Stern-Garlick experiment. No one for an electron. And so it's funny, this 97 letter of Batlan attracted, letters in reply to the Journal of Physical Review. I'm not going to talk too much about that, but it's funny. It's one of these things again where everybody knows what his experiment should yield and will yield, and I know it too. But it just hasn't been done. But it just goes to it would provide more of a basis of what I'm talking about here. Like, yeah, there is a plane of oscillation of that charge, and how does it behave? These kind of experiments. So now we're gonna move to actually the topic that I wanted to talk about is these wavelengths, the Broglie wavelength, the Compton wavelength. And here we have you will say, oh, that's the lambda there, right? Well, no, I said the Compton wavelength is the circumference, is a circular length, length as we measure it along a circle. And there we have a lambda, which is, as said, the distance between two successive points in space, where the phase of our complex valued wave, our wave in 2 dimensions, is the same. Well, it's not the same because we have the time, but the wave function itself has the same value. Its vertical and horizontal component are the same. So our wave function has the same value. And so, yeah, because our wave goes through a cycle and has a cycle time, and so the wavelength, frequency, cycle time, these things are all related through the velocity of that wave, which is special. But yeah, it has a velocity. Our electron moves, in 3 dimensions at the same time, along the x-axis and along the y-axis and the z-axis. So we have a 3-dimensional wave in 3 dimensions here, and we can measure that lambda. And now well, I'm gonna skip this because otherwise you really will fall asleep. It's 2 hours and a half that I've been talking now. It's a bit long for me as well. Here, basically, what I do below is I establish the relativistically invariance. I show that the argument of the wave function theta, which is 1 over h bar times the energy of our particle, which depends on the velocity, so ev times time, minus the classical momentum, depending also on the linear velocity, times x, the position of our particle along its linear motion. And so then you can go from one reference frame to another, but I show there basically, that theta If we would measure it in the reference frame of the electron itself, we have the energy becomes E0, and the 0 is the subscript in the stationary reference frame. We divide it by h bar, and we multiply it by the proper time, t prime. Yeah, it's theta, and these are the Lorentz formulas that I put there, and so we can go from our moving reference frame to the stationary, from our reference frame, which is the moving one, and relative motion to the electron, to the reference frame of the electron itself, and we can go back and forth using the standard Lorentz equation. So I'll let you go through this by yourself. I'm just noting here, it's sort of this thing, equations. Why do I put them there? It also shows that, yeah, the Planck-Einstein relationship is relativistically invariant. In whatever frame of reference we are, Planck-Einstein relationship is the Planck-Einstein relationship. And that shows us actually that these are the real laws. Why I'm saying that, uncertainty principle, you know, uncertainty in position, uncertainty in momentum, these are, they depend on our reference frame, position, you know, time, momentum. These are things that vary. When I'm in one reference frame, I measure a different momentum, and also, you know, distance and time and all. It becomes all, you know, it varies. But the fundamental law is the Planck-Einstein law, and that's valid regardless of the reference frame. And this is also where it shows that the argument in my wave function will not depend on the reference frame. The phase of my wave function is relativistically invariant. So that's also a reason why I'm saying that the phase and the wave function is much more fundamental than the wave equation, which we use to sort of, you know, come up with some kind of description of reality, and then we say the solutions to this wave equation are representing particles. No, the wave function itself, the particle itself, that's real because it doesn't change going from one reference frame to another. Okay, let's further think about now the physical meaning of the de Broglie wavelength. I will let you surely read as we said. The wave function is a bit of an implicit function, right? For each x, we have a t. When we think about a wave function modeling a particle, we'll say, you know, it's at some position x at some point of time t. So it's an implicit function. For each x, we have a t, and you know, at some point of time, we have, you know, we think of our particle being somewhere. So we have so we don't have actually uncertainty here. We think of our particle as being somewhere at any point in time. You know, at this point in time, it's here. Another point in time, it's there. And the relationship is then given between the two by our very classical, you know, velocity. You know, so we'll get some linear motion, right? At the same time, we have our wave function and the elementary wave function, which I write out there. You know, we have is the amplitude times the Euler's number with the minus the imaginary exponent with the phase, and the phase is yeah, p times x divided by h minus e times t, the plus or minus for the imaginary unit. That depends on you know, convention, and I talk about it also, convention and quantum mechanics in my papers. I'm not going to do that here. But yeah, if you look at that, I mean, here I'm writing it as a, you know, indeed the sum of a cosine and a sine, but I put the imaginary unit there to make sure that, you know, our sine is interpreted as a vertical motion, or at least a motion that is perpendicular to the cosine motion. So we can think of pxh, well, px divided by h bar as a phase factor, and then we actually do get our de Broglie wavelength out of this. So, but again, how do we interpret this geometrically? Again, so we get the de Broglie wavelength, all right. So I'm getting a de Broglie wavelength. De Broglie should, I mean, you guys also shouldn't be thinking that I'm doubting the Broglie relationship. No, I'm not. The Broglie wavelength is sort of like a, yeah, a bit of a phase factor in this thing, but so Geometrically, how do we represent? Is it the same lambda as in that left-hand figure? No, it is not, because yeah, I said lambda can't be. Again, the h divided by p, if the momentum, the linear momentum is zero because the velocity is zero, then it becomes infinity. And so the lambda becomes infinity. I showed you the figure on the left there. When our electron is not moving, that lambda is actually zero. It's not infinity. So the lambda in the lambda is h divided by p is not the lambda that I showed there on the left hand, the distance between two crests. No, because that lambda becomes zero when the momentum is zero, when our electron is not moving. And so, well, we can do a lot of philosophy, but you really should play with these, and I'm going to do that in a moment, actually, play with these equations. The one thing I want to point out here is a bit, and that's sort of a general something for you to think about, is that momentum actually is a vector quantity. It has a direction, and a particle is moving in some direction, and so that's actually where, if you think through the logic of that of the Broglie's relation, you should logically say like lambda, the Broglie wavelength, if it's equal to Planck's quantum of action divided by the momentum, the linear momentum of our particle, then we should write the Planck's quantum of action as a vector quantity. You'll say, well, what is this? Well, it makes sense, right? Because the physical dimension of Planck's quantum of action is a force times a time unit times a distance. So a force also has a direction. So there's absolutely no problem whatsoever in writing, Planck's quantum of action h as a vector and the whole and the Broglie relationship as some kind of vector relation. I'm noting how it's equally simple, like mass, Newton's formula. This is actually relativistically correct, then, because mass is the mass of a moving electron, or it's m0 or mv, but it will always be equal, as I said, as a measure of inertia to the ratio between the force and an acceleration. And so see, the force and acceleration, usually we just treat them as scalar quantities, but actually both force and acceleration are vector quantities. It's a force in a direction, and acceleration will accelerate it in some direction. So going further on that logic, and that's something else that's very surprising in mainstream quantum mechanics, is like I don't see that the uncertainty principle is always expressed as sort of the product of two scalar quantities is equal to h. But the uncertainty, if we do, I mean, this model, we could introduce uncertainty, but the uncertainty that would be in this model would be in the direction of the plane of oscillation of my point-like charge. Yeah, actually in the angular momentum vector, because the angular momentum vector, as you know, that's a polar vector, will point in some direction. So if my plane of oscillation sort of wobbles around at some kind of different frequency, maybe, or not at all, or just because it snaps into position when we move it through a magnetic field. In any case, the whole idea is that the uncertainty that we think is in the momentum, it could be in the direction of the momentum, and that's what I put there. I have the real p, the black arrow, which is in one direction, and we measure that, but yeah, maybe what's going on there is we have some kind of something fuzzy word subvectors, and then we're not quite sure what the direction of the vector is. So it's just an idea. I'm not developing it here because I have confused you already enough, and I want to stick to what it is. I said, but I'm not excluding that we do have a chaotic movement there, and that there's uncertainty, but it's going to be a different type of uncertainty than this undefined uncertainty in mainstream quantum mechanics. So here I said it that we cannot interpret the length, this linear distance between two crests or two troughs, as the Broglie wavelength, because for the momentum being zero, the classical velocity goes to zero, we have a division by zero, and the lambda is h divided by p, the Broglie relation, and we get an infinite value. And then the funny thing is, I said, when v goes to c, we get a lambda for the Broglie wavelength that is equal to the Compton wavelength. So how should we interpret that? And then well, I put it here. As soon as our point-like charge starts moving, has to cover some horizontal distance because we are moving with respect to the electron, or the electron is moving with respect to us. It doesn't matter. If we're in our frame of reference, the circumference of the rotational motion must decrease. Because yeah, it needs to cover some extra distance, right? Regardless in this moving reference frame, it has to cover some extra distance, linear distance. And then so that's actually fine, because if we drop the subscript 0, we have actually a Compton radius that varies, that depends on our reference frame, that depends on the velocity of our article. It's just h is h bar divided by mc, and m is relativistic mass here. It's not m0. If it moves, the mass will increase. It's the relativistic mass formula. So and we know that h divided by mc is then the Compton wavelength, but the Compton wavelength here also becomes a variable quantity. It depends on our reference frame. And so how can it do that? Well, it's easy. If the electron moves, it will have some kinetic energy. We must add that to the rest energy. So the mass m in that denominator, mc, increases. And h and c, I said, these are the real physical constants. We measure them always the same. H is h and h bar is h bar, because we divide by 2 pi, and then c is c in every reference frame. So a must decrease because our m increases, because these are relativistic. They depend on our reference frame. So how does it work with the frequency? Well, it's very easy. The frequency is proportional to the energy. So while energy also increases, and the frequency must increase, and so the cycle time t must then decrease, and so it all makes sense. We have a smaller radius of that orbital motion, and it covers the smaller distance in less time, and these equations all make sense. So we're going to continue these calculations. I put that there and said what happens really is this Archimedes screw that you see there is it gets stretched when v, the classical velocity, goes up, and that's where we get a first formula. Don't worry, I mean, it's 2 hours and 45 minutes that I've been talking. I'll finish around after 3 hours. This is a 3-hour presentation. I said you can pause, but I don't. Look at that thing here, lambda. Lambda is the distance between those two crestal waves. I said because this is like a 2 or 3-dimensional wave, 3-dimensional wave actually. In 3D, I'm talking 3D spatial dimensions here. See, it's the classical velocity v times the cycle time, right? When it moves from the beginning of the thick black arrow to the end point of that same arrow at lambda. That's the linear velocity of our electron, of the point-like charge, v times the cycle time, because at the beginning point, end point of the arrow, I mean the arrow has 2 arrow points, lambda, the wave function will have the same value. I'm talking here a complex valued function. The horizontal and vertical component are the same. So cycle time is is 1 over f, the inverse of the frequency, and then we use the Planck-Einstein relationship, so it's v times h divided by the energy. So that's the energy is mc square. So we get v over c times h divided by mc. So we just c square. We split it into c times c, and so this is an interesting formula because I get that linear length lambda, which I said it's not a Broglie wavelength, it's also not a Compton wavelength, but we clearly see it's beta times the Compton wavelength. So that's really interesting indeed, and we get what we know is true. If the velocity of a linear classical velocity of our electron is 0, the momentum is 0, then that linear length will be 0 because beta is 0, and 0 times the Compton wavelength is 0. So that's already quite good because we have a sensible thing there, and it's also, of course, if the speed of our electron goes to c, The linear velocity, the classical velocity, goes to c. I said it can't because we have a rest mass for an electron. There's energy in that orbital motion, so it has a rest mass, and it's pretty. I mean, an electron compared to a photon is pretty massive. So it will never go to c, be beta. But if it does and gets so close, and it would go really all the way to c, then it becomes equal to the Compton radius, that lambda. So lambda will be equal to beta. Beta is 1 times the Compton wavelength. So, but then you look at that figure, you see that red thing, you stretch it and stretch it, your Archimedes screw. At some point in time, you can't stretch it any further. You've used all the available wire in that spiral or whatever. So, well, in that circle, and so your circumference of the circle, of that black circle, just becomes a linear length. So that's sort of where this electron model links up with a model of a photon. We don't talk about photon models here, but I have papers on that too. But it links a bit the two. At the same time, you need to realize here we're talking matter particles, and so my basic theory of reality, or whatever you want to call it, is there's matter and there's light, right? And matter involves charge. There's a charge, so that charge is well, what is it? It's charge. It's just charge. I said that point-like charge has no mass on its own, but the electron as a whole it acquires some rest mass because that charge is oscillating in this Bewegung. So now we need to go back to our well, we don't need to, but we will go back to the Broglie wavelength, which is h divided by p. So we see that at the bottom here, we rewrite the Broglie wavelength in terms of the Compton wavelength, and so how do we do that actually then? So it's h divided by p, I said, the Broglie wavelength. I use p instead of like an L for Louis or something, because the Broglie wavelength is clearly a function of the momentum p, right? So that's why I call lambda p. So it's h divided by p. And so that's h divided by the mass of the electron, which is the relativistic mass. It's the rest mass when the v is 0, and it increases as v goes from 0 to c. So then I add 1. I can write 1 as c divided by c. So using one of those c's to rewrite c divided by v as beta, I get h divided by mc times 1 over b. So h divided by mc is the Compton wavelength, lambda c divided by beta. And so then I can actually, that's sort of, okay, I said this Compton wavelength, we can look at it as a circular length, length measured over the circumference of a circle when it's that black thing. But I can also look at it as a linear thing when we stretch and v goes to c. So on the left, I have h divided by mc beta is equal to the Compton wavelength divided by beta. But on the other hand, I can say like, okay, I keep my beta, but I rewrite my Compton wavelength again in terms of the rest mass of my electron. And then I know I need to use the Lorentz factor. So to go from lambda c over beta to 1 divided by the Lorentz factor there, which uses a gamma as well, times beta, times h divided by m0, the mass of the electron, the rest mass of the electron, and the mass of the electron in the inertial frame of reference, times c. I get that the Broglie wavelength is equal to 1 divided by gamma beta on the Lorentz factor times the relative velocity times so h over m0c is the Compton wavelength, so I can write it as 2 pi times the Compton radius, a0 on the Compton radius as measured in the inertial frame of reference, in the frame of reference of the electron, so when velocity is 0. So look at that. This is really very simple math, but it's quite deep. And yeah, so 5 slides to go. Yeah, I'm sorry, I didn't invest a lot in sort of shortening text here, but I take the same equation. So the lambda p is the Broglie wavelength, and the derivation is there, so you can recheck it a bit. But it's equal to 1 over gamma beta times 2 pi times A0, the Compton radius of the electron at rest, h divided by m0 c. So it's a how does that function behave? Well, it behaves like we see on the right hand thing there. We know that Broglie wavelength, it will start. So at the x-axis here we have 0 going to 0.5 to 1. So what is that? That's the relative velocity. Huh? So my variable there is the relative velocity. So in reality, relativity theory tells us that beta has to be something between 0 and 1. But mathematically, okay, we might imagine superliminal velocities, but they don't exist in reality. So the domain of this function is really between 0 and 1, but I'm plotting the curve for values that are even larger than 1, like 1.5 there. That's where, as far as I go. So then I plot the Lorentz factor in the red. So y, that's the 1 over the inverse of the Lorentz factor is a circular arc. You know that, you've seen that when you're looking at the Lorentz formulas and these transformations, standard course. So we have a circular arc. That's the red function, very easy, and so that makes sense because the Lorentz factor is Lorentz factor, and so yeah, velocities, relative velocities must be between 0 and 1. The 1 over beta there is a bit funnier. That should also be a function between 0 and 1, but that blue function there, I let it go a bit further, but the domain also is between 0 and 1, and you see that that function goes from infinity if beta is 0. 1 divided by 0 is infinity, and then it goes to 1 divided by 1. So when the classical velocity of the electron is 1, then it's 1 by 1, so it's 1. So then we need to take the product of 1 over gamma, 1 divided by the Lorentz factor, 1 divided by the relative velocity. So we have 1 divided by gamma times beta, and that's the well, I would say that the Broglie wavelength, but it's sort of the function that it's like an envelope. Well, the 2p a0 is like the envelope, and this modulates the envelope function. So the 1 over gamma beta factor, that's how it behaves. It goes from infinity to 0, and that you need to multiply by the envelope function, which is 2p a0, and that makes sense. That is how the Broglie wavelength really behaves. Now, that's nice. That's good. That sort of makes sense mathematically, but I still haven't done what the title slide says. I would give you a geometric interpretation of the de Broglie wavelength. So the Compton wavelength, you see the geometry of that. You see what it means in space. That lambda, that linear wavelength between two waves or crests, you see what it is. But the Broglie wavelength itself, geometrically, I told you how it behaves now mathematically because of that 1 over gamma beta factor, but I haven't shown you what it means in 3D. So here I'm actually, doing a bit of a recap. So we said the Broglie wavelength will be equal to the Compton wavelength for VSC that we know, and I show that y again. It's only equal to the Compton wavelength if the velocity v is equal to c, and then we have that relationship between this linear, the new wavelength lambda, the distance between the two crests, and the Compton wavelength, lambda is beta times lambda c. And so we get these two results. Again, look at it carefully, read it, but it works out. The Broglie wavelength times at lambda is equal to the Broglie wavelength times beta times Compton wavelength. So I substitute, and I really get this funny result that the beta actually cancels out, and I get that the product of the Broglie wavelength and that linear wavelength is the square of the Compton wavelength. You see that? Lambda p times lambda is equal to lambda c squared. So that's nice. I can also take a ratio of any of these three wavelengths. You can play with them. It doesn't matter where you start in that triangle. We have three wavelengths, and we multiply two, we'll get the third one. And so this is the interesting. Here I'm looking at how these three different wavelengths or lengths, circular linear distances, or something in between, are related, and you will see why in a moment, because I will relate it to a very nice mathematical shape that you will recognize and you can work with. So the lambda is again the beta times the Compton wavelength divided by lambda p. I forgot a subscript there. Sorry for that. And then you do the substitutions, because the Broglie wavelength we can substitute again by h divided by p. So because we have the Broglie wavelength in the denominator, it's p divided by c, and then beta is v over c, and then my Compton wavelength is h divided by mc. So we have mc squared. The momentum is, of course, the mass times the velocity, the classical velocity. So I get mv squared divided by mc, because my two h, they cancel out, and so mv squared divided by mc squared. So my m cancels out in the numerator and denominator, and I get v squared divided by c squared, which is beta squared. So it's fascinating, actually. I can geometrically, if I want to make a representation or sort of describe that wave, our electron wave, or the electron itself, that point-like charge going around, moving through. I have like three wavelengths here, but they're, and you may say that's hugely complicated, but they're related to each other in a very easy way through the relative velocity. It's just, I just have that beta square. So what is this? I mean, it's remarkably simple mathematically, but it's you're still like struggling with this thing, like what is it? But it is nice. It is nice. I have three wavelengths, and I said I made a mess, but actually I didn't. I come to a very simple result now. All depends on this velocity. So which makes sense. I'm in a reference frame, my reference frame, and I want to make sense of that shape of a wave of an electron, and in the end I get something very simple, beta squared. So let's move, because we have mass there, and well, velocity, let's think. Velocity, beta is a relative velocity is nice. That's a number between 0 and 1. So that doesn't depend on our units, but yeah, when we want to go to a geometric interpretation of that wave, we really need to think sort of, time units, distance units maybe, and then h and c, and what does it all mean. So maybe there we want to move to natural units, where we say, okay, h is a quantum, right? And velocity in a way is a quantum as well. It's very large, the speed of light, 298,000 or 299,000 meters. I don't know the 8 digits by heart, but it's a very precise value, but it's very large because our time unit is large as compared to our distance unit. It's one of those things that I want to stress here, because people often think like, oh, the magnetic field vector is not important because the magnitude of the magnetic force is 1 over c times the electric field factor. But no, it's just, I mean, c is a large number because of our time and distance unit. If we measure distance in you know, in light seconds, you know, the distance that is traveled by light in 1 second, then c becomes 1. And so what does it mean in number? It really depends on our space and time units on what we choose to measure, and that's something that has to do with scale. You know, I'm large, I'm big, and I will become 70 years old. Atomic physics, particles have much smaller lifetimes and this and that. So that's where natural units, you know, it's nice because they show things that you don't see when you're not using natural units. And the same thing actually for Planck's constant, the quantum of action. We may think of it as a very, 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 very small unit, you know, when we use the standard SI units. But if we have natural units for time and distance, we fix them. And I said you can fix them in a number of ways. There's not one natural unit, but you know, we establish time and distance units such that the proportionality between them for you know, when we measure the speed of light is equal, that we get at the speed of light is equal to 1, then we can use that using the Newton's force law to also establish some kind of natural mass and well, force unit basically. And so then we use a force unit, and we can choose that also such that Planck's quantum of action becomes equal to 1. So you say, how do you do that? Well, it must be big force, right? Or a small force. Well, it's a bit subtle, because I said you can choose your time and distance units, but you know, I'm not going to go here in too much theory, but the bottom line is, you know, we can choose our distance and time and force and our units such that Planck's quantum of action is expressed as you know, being equal to 1, and the equations will work. The physics are just as good. Reality is the same, and our theory is the same. But we have H and C is 1. I'm saying, you know, H and C are like a quantum, because that's the thing also when people ask me, so well, what is this quantum thing, and what is quantized and what is not? It's like natural constants, probably you should think of as a quantum. Planck's constant is a quantum, the elementary charge is a quantum, C is a quantum, and that sort of then leads through, yes, a quantization of space, if you want, as expressed in our electron that occupies, you know, a very specific area or surface. You know, think of it as a bit of a surface describing that charge. So, but the real quanta, the real quantum, so quanta, are natural constants. So before I move to the next slide, again, you know, or this two-dimensional wave, it doesn't have any real crests or troughs, so lambda is just that distance between 2 points whose argument is the same, except for a phase factor, you know, equal to n times 2 pi, and then, you know, it depends on your time unit, on and the velocity and how you measure these things to get that phase factor, 2 pi, 4 pi, 6 pi. And then the other thing, and that's kind of important, and I don't want to confuse you too much, but the other thing is also, like, yesterday in my presentation, somebody said, okay, lambda, why don't you give it an L subscript? You know, you didn't use the L for Louis de Broglie. So, and it's a linear distance in the end, is it? Yeah, it is and it isn't, but I want you to remind that plane of oscillation, it's kind of neat when we sort of choose it to be perpendicular to the linear direction, the linear motion. But it can wobble around as well, you know, when there's no external electromagnetic field, you know, it can be in any direction. It's only when it goes through an electromagnetic field that it will sort of line up. And then, you know, when there's no external electromagnetic field, then it can be anything. And we don't know, because yeah, as long as we don't establish an electromagnetic field, we actually don't have a real frame of reference. How do we measure things if we don't have sort of some kind of electromagnetic field to refer to? But these are philosophical remarks in any case. So I did pass 3 hours now, but we're almost there. So if we redefine our distance, time, and force unit by equating C and H21, and then our Compton wavelength, which I remember you know, is a circumference, but a circumference that becomes a linear distance when, you know, velocities goes to C. So it's something in between a circular and a linear length. But this is the Compton wavelength. Then it's 1 over it was h divided by mc, remember, right? But h is 1, so I have 1 in the denominator, and then I had mc, but c is 1, so I'm left with m, so it's 1 over m, and 1 over m is equal to the Lorentz factor times the rest mass. So the Broglie wavelength, I said that was 1 over beta times the Compton wavelength. So that becomes 1 over beta m. The Broglie wavelength was equal to 1 over beta times the Compton wavelength. So it's 1 over beta m. So lambda then, that linear length was beta, not 1 over beta, but beta times the Compton wavelength. So that becomes beta divided by m, or beta divided by Lorentz factor times m0. So the three lengths are really, the formulas for our lengths become expressed as a function now of m and the mass of the electron and beta. And you say, oh, can't you equate m to 1 as well? Sort of choose, no, because m is really depends on our reference frame. M is a relativistic mass concept, so I can't reduce this any further. What I can do then is again, multiply a few things and divide these three wavelengths and again look at that relationship which we had, which is the Broglie wavelength times that linear length is the squared Compton wavelength. And what is the square Compton wavelength then? Well, that's actually the one formula for the Compton wavelength where beta does not appear, and so it's 1 over m squared. And you'll say, okay, fine, so what? You are very tired now, and I'm very tired too. But this is very deep. We have an expression of a shape. We were trying to model a wave here, and I showed you how that wave looks like. We had a circular current, a current ring, when our electron is not in motion, when it's standing still, and then it becomes this Archimedes screw. When I mean, the trajectory becomes the Archimedes screw when it picks up some speed, some velocity, when we accelerate it in an accelerator, or when it comes out of one of these primitive X-ray cathode generating electron beams in 20s. You say, okay, fine, nice formula. Still, you didn't do, give me a geometric interpretation. I said, I gave you one. You see the shape of that wave. And the other geometric thing that I want to give you here is look at that formula. We have, two lengths that are linked, that are equal to a squared length, and that's the Lattice Rectum formula. Lattice Rectum formula for an ellipse, which was discovered by Leibniz. Leibniz, I mean, that guy is like Euler. And other mathematicians or Renaissance guys, Da Vinci, and they did so many things. And that's one of his other formulas, a bit less well known, but he did the Lattice Rectum formula. Ellipse is intriguing, an easy and a difficult figure at the same time. If you look at that ellipse, you look at the point between the two focal points, for instance, F1 and F2. If you compress that ellipse sideways, you let the focal points F1 and F2, you let them merge into the center, then you get a line, right? F1 goes to C and F2 goes to C. Just get a line. Your ellipse collapses into a linear feature, a line, and the length of that line will be 2 times B. You can see that, right? And so, and if you but if you don't compress it, actually, on the contrary, you stretch it and keep stretching it and keep stretching it, B will become smaller and smaller, because if we want to keep the same circumference, but we want to have a larger distance between the focal points between F1 and F2, so we move F1 to the right and we move F2 to the left, then B must become smaller, and so B squared will become smaller, and that means something must happen with A, with the Broglie wavelength, and something must happen with that distance P, the distance between the focal point and the perimeter, or the circumference of the ellipse. So that's what happens with these wavelengths, and it's described by Leibniz formula for an ellipse. I mean, he had a number of formulas, but this is a very, I would say a basic one. It actually summarizes a number of other formulas for an ellipse. The funny thing is with an ellipse, for instance, it's a funny figure because we have an exact analytical formula for the circumference of a circle. We don't have an exact, it may surprise you, but you can look it up on Wikipedia. We don't have an exact analytical formula for the circumference of an ellipse. So it's kind of funny, but it's deep at the same time. Yeah, I'm tempted to say a bit more, but this is crazy enough already, right? Two more slides, the summary of results. Well, that's what I have here. Sort of my geometric interpretation is this one. So you have that very complicated shape of a wave in 3 dimensions. That's our electron, and that shape is it depends on the motion, on the linear motion, the classical velocity of our electron. So we have, it's going to be the black thing, the ring current in a plane, and it becomes, the trajectory becomes something between a circle and something linear, purely linear when speed goes up, an Archimedes screw. So that's an intriguing geometrical feature. And then it goes on. If speed goes higher and higher, it becomes something. We get a linear wave. Linear wave again, where the point-like charge doesn't disappear; it's still there. It just moves linearly, and it will still have some spinning motion and everything. So that's where then this model, you can think about the intrinsic properties of an electron, which in mainstream quantum mechanics are just like they emerge from nowhere. Here they emerge from something. Clearly we have a charge, and you can sort of add features. I said the anomaly in the magnetic moment can be explained because that point-like charge will have, very, 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 very tiny dimension, because the Compton radius is already very small, but the point-like charge itself has a smaller dimension. So you can add and add and add on this model, and it all makes sense. That's what I found in the last 10 years or so. It all makes sense. So on the right hand side, I have a Lattice Rectum formula, which sort of shows that as complicated or simple that geometry is, depending on your point of view, on what you think is complicated and simple, it is related through very nice geometric figure, which is an ellipse. And here again I show at the bottom, the simplest things can get quite complicated. This sort of, we think waves in 2 dimensions already. You can model almost anything in 3 dimensions using very simple relationships like the ones we presented. Yeah, there's, what I want to say here is my last slide, because people ask then, how do you predict stuff, and what are the implications? And so what do you want to explain? Can you explain? Should be explained to confirm your theory? Is well, it is this actually, where I'm basically going like, okay, fine. There's a lot of work to be done, and that's sort of where it's so sad that 90.99.90, well, let's say 99% of brains in physics and mathematic departments, or at universities, people waste their time on looking at very elaborate theories, and deriving another theorem out of some theory, working on Bell's theorem, proving it, disproving it. But these mathematical theories are just like, for me, there's something very obvious. Rather than looking at Bell's theorem, saying, "Well, what you're saying can't be true," because for me, Bell's theorem, let's be very clear about it. Bell died, and he himself said that before his death, like, I hope someone disproves my theory, but probably it won't be possible to disprove my theorem, because why? The axioms, it's garbage in, garbage out. You need some kind of radical, that's what he used actually, he didn't say garbage in, garbage out, but he said you need some kind of radical new concepts, conceptual renewal, he called it, to just get rid of my theorem. So I don't want to, I'm surprised people spend time on reworking, representing mainstream quantum theory, rather than doing what needs to be done, and this is this here, we have fine experiments, beautiful experiments, you know, who are actually measuring, because now the nanotechnology is available, you know, these interference patterns. And I said, look at the figures in A, diffraction when electrons go through one slit, and the C, you know, what you see on the screen, and then the sort of the idealized or the intensity distribution, C3 there, and you know, that goes through the other slide when we close the first slide. And then we bring these two together, and what you see there is a very basic. Basically, it's a superposition of two diffraction patterns, but we do have, you know, some interference going on. So that means actually that when we open two slides, there is something going on in the two slides, and it's not a big deal, because you can really see, I mean, you really need to make it larger. You see these little Fraunhofer things like absorption, or some frequencies get reinforced or reinforce each other, and some like get absorbed. And it's those tiny little things, they probably have to do with these, I said, these very high frequency of our electron, the Zitterbewegung, and then, you know, then you need to start thinking about, you know, what is that force. And Heston has basically said, you know, the Zitterbewegung electron, it's like a superconductor. It's the nature's most fundamental superconducting loop. Electrons go round and round at very high frequency, and, you know, because it's a current ring, it generates an electromagnetic field. And yes, theoretically, that's what happens there. You know, you have a perpetuum mobile, and it's like a superconducting ring, but there's a number of drawbacks, because yeah, that's fine. I was in touch with David Heston, and yeah, what keeps that orbital charge then, you know, in charge? If we don't have like a real wire in space, like you do have when you're doing an experiment with a superconducting loop. So there's a lot of questions there that you need to ask, and you should ask, and then you need to think about it. I said the mystery has not gone away. It just like shows that you know, thinking in terms of paths and their lengths, and then associating a wave function or an amplitude with these paths, and then adding and whatever, it's not the way to go. The Italian researchers, the research groups from Modena, Bologna, Palermo, you know, they're doing the right thing. And they think like, okay, fine, what shape of wave would produce an interference pattern like that? And that's where the work needs to go. And I think that my model might show. It said it's sort of a flexible model. It's just to describe that wave. We have like three wavelengths, but they're not random. They're linked to each other through very easy, you know, the mass of the electron, basically, relativistic mass. And so yeah, going from my model to, you know, describing what happens here, that's the way forward. And with this, I've reached 3 hours and 20 minutes of talking, and my throat is rather dry. So I will quit here and push the stop button, and I don't know if you're still there, but have fun with it, play with it. You can find my email and contact if you're really intrigued by this stuff, and you can mail me. And don't have an awful lot of time. I have another day job, but I usually do reply to mails, basically saying like, okay, fine, think of this, think of that, or basically saying like, this is very interesting, but I don't have time to look at it now. I might get back to you. So please do mail and look at it, and the most important thing with these things is go through it for yourself. If you go to my papers, I also have, you know, and I'm not an academic, I do constantly challenge myself and say like, okay, this makes sense, this doesn't make sense, you know, there's something weird here. So I do have it in my papers too. People ask me like, how do you think then about these oscillations? So is it the space-time oscillation? I don't want to go there, but I do have like an idea of what antimatter might be, and that would probably involve like, you know, an opposite space-time signature, as I call it. So there's more mystery behind this thing. And then, you know, when we look at proton models and other stuff, you know, stuff pops up, questions pop up, and but again, this theory of mine does allow us to approach these questions in a very sensible way, which we can sort of visualize or imagine what we're doing, and what actually what the model is about. So unlike working with wave functions. So thank you again, and I wish you a wonderful day.